Okay, I think we can start this session. Am I audible first of all? And hello?
Yes, yes.
Okay, so I'm audible, and hopefully you can also see the screen, my computer screen.
It is not coming on. Wait.
It's not, I have shared it. Should I stop and again share it maybe? I'm stopping it and then again sharing it. Okay, now?
Yes, now it is coming.
Okay. So, welcome you all back to this event, the second session of our IDL-2020. My name is Gagan Kumar, and I'll be chairing this session along with Professor Amrinder Kumar. So our first talk will be by Professor Kishan Dholakia. Just let me introduce briefly about Professor Kishan Dholakia. He is working in the School of Physics and Astronomy at the University of St. Andrews, United Kingdom. Professor Dholakia is the Fellow of OSA and the SPIE. He is also the Fellow of Royal Society of Edinburgh. His research interests cover pretty much everything related to optics. He has won several awards, including EPSRC Public Understanding of Science Award in 2004, Photonic Club of Excellence Prize in Photonic West, USA in 2005, R.W. Wood Award in 2016, and also he is the recipient of European Optical Society Award in 2003. So now he will be speaking on Let Nothing Slow You Down, Optical Trapping in Vacuum. I request Professor Dholakia to kindly share his screen and please deliver the talk. I'm just stopping here my screen sharing. Yes, please.
Okay, thank you. I hope now you can see my screen. So my name is
Yes,
Kishan Samakia. I hope you can all hear me clearly.
yes, we can hear you and we can see the computer screen.
Thank you. So firstly, it's my pleasure to present today, and I appreciate this opportunity on this very auspicious day to be part of your exciting event there in India, and I hope you will find the next 30 or so minutes very interesting. So I'm going to talk about optical trapping in vacuum. I work at the University of St Andrews in Scotland. As you can tell from my appearance and my name, I am not Scottish. I have an Indian background. My parents are both from Gujarat, so this is especially nice of me and helpful for me and exciting for me to present to students and colleagues and staff back in India on this day. So this is St Andrews. This is where golf was invented. If you can see in the top, and it's a very small town in Scotland. If you have any questions, I would please answer them at the end, or you can send me an email as well. And we have a Twitter website and a web page, as you can see. Let me first say something about St Andrews, where we are. Many of you may not know. It is where future King and Queen, William and Kate met. St Andrews is in the north of the United Kingdom. You see there on the map, it is about Edinburgh to London is a 1-hour flight. And so we are 1 hour driving from Edinburgh, so we are there, about 500 miles from London. It is a small town with only 15,000 people, and when the students are there, it's a further 9,000. But it's a very nice place to live and work. And there in the top right, you see the complex, which includes the physics department. It's in the bottom, and on the top left, you see the golf course, which you see again on the bottom left. St Andrews has a very long history. It is the third oldest English-speaking university in the world, after Oxford and Cambridge, and recently has done extremely well in research and teaching awards, and is currently the University of the Year in the UK, named by the Sunday Times. So it's a lovely place to work and do science and also liberal arts. But that's a quick introduction to the university. My group works largely on shaping light. I'm interested in many things. These are some of the things that we do in the group. I don't have time today to talk about all of them. You can find more details on our website, or you are welcome to drop me an email. Basically, what I'm interested in is the use of optics for advancing our understanding of the light-matter interaction. And what I would like to do is particularly to see if we can enhance our understanding with shaping light. This means going a little bit beyond a simple Gaussian laser beam in terms of both polarization and structuring in space and time. Examples in our group, we will talk about the work in the top left and the top right, we will talk about today, but in the middle we have new work using imaging in time to go through tissue, and at the bottom you see the zebrafish brain imaged with different light beams showing incredible high resolution on the right, compared with what's the airy beam compared with a normal beam, a Gaussian beam on the left. So we have wide-ranging interests, and you heard already talks today on microscopy. So this talk will be not on that, it will be on the manipulation area, which is something I would like to share with you today. So light is incredible. One may say even that light holds a privileged place in our universe. The only constant perhaps we really have is the speed of light across the whole universe being c. But also when we think about light, we might think of laser damage, we may think of imaging, but we never really think of the force of light. And this image you can see here shows various images both from reality and also from science fiction that says light can maybe exert a force. And we know in physics, if we wish to exert a force, we need momentum. Now, some of these ideas are very exciting, and we go home and watch a movie on Netflix or some other channel, and we see exciting ideas of light, cutting objects, moving objects, but rarely do we think this can happen in the laboratory. But I'm here to tell you today that some of these ideas are actually true. And they're true not at the scale as you see there of a ship or a planet or something that we might understand in the macroscopic world, but mainly at the mesoscopic world. So sizes of the size of a cell and smaller, we can indeed exert forces with light and use them to move and understand objects very, very well. This is exciting not only for the things I talk about today, but even in space exploration. NASA, for example, are using so-called tractor beams for tracked sample gathering, but this is very challenging. So today I'll give you an introduction to this area and then tell you a little bit about the excitement in vacuum, which is one of my current areas of interest, and I hope you'll find this interesting too. Where do we begin with the force of light? Well, we go back to 1619, just over 400 years ago, to Johannes Kepler, who with Tycho Brahe did the understanding of the laws of planetary motion. And here we see the idea that we have a tail of a comet going around the sun. And you see here, this actually goes back to Arpian in 1577. And Kepler wanted to understand this tail of the comet. And you can see here that the tail kind of points away from the sun. It doesn't exactly, it's a little bit more complicated than this simple picture on the right shows. But basically, it never points there. So he wanted to understand this, and he thought, as he wrote in the paper then, that somehow the sun, the rays of the sun hit the comet, and they caused some track of light, and the comet breathed its own tail out. And here on the left, we see a drawing of Helvelius and Aristotle and Kepler meeting with the comet ahead. Now, this, in fact, is really more or less true. So the radiation pressure from the sun can actually cause the tail of the comet to occur. And this is actually something that we actually now take for granted. But of course, we don't have the sun. So what we really need to do is think about how we can maybe do this on Earth and where we can use this concept. Radiation pressure goes back to probably the greatest Scottish physicist, James Clerk Maxwell, who was recently was honoured at his parting place not far from St Andrews in Scotland. And Maxwell, even with electromagnetic theory, computed the radiation pressure of the sun on illuminating on Earth. And he says, maybe if we could make an electric lamp or something and then maybe illuminate a little disc, maybe suspended in vacuum, we could see a mechanical effect. Now, this actually goes back over 100 years to the work of particularly Nichols and Hull and Lebedev, and this led to what's a kind of device like a Crookes radiometer. You see these veins here in the jar, and many of you may know this device, but regrettably, this device actually does not go around in the way that you expect, unless it's in vacuum. So for those of you who know, you have a shiny surface and a dark surface. You can see there inside the glass, but it goes around counterintuitively because we also, with the heat, the light of the sun also causes thermal effects, which actually causes the vein to rotate in the wrong direction. And only in a vacuum does it actually go around in the correct direction. Anyway, they did resolve this and they did use this device. It's a beautiful experiment and you can try it. I'll buy one now online and think about it. But again, it was very difficult to do anything more practical with this, following on from those studies. Let us quickly take a look at where this momentum of light may come from, because it comes from the idea of the laser. So let me just show you an example. If we have a rubber and aluminium bullet, both of the same size, speed, and mass, and they fire a wood, you, as a student, you get asked this. This is an excellent question for understanding momentum and forces and energy. In other words, which would most likely knock the block over, a rubber, aluminium, or the same, and which would damage the block, rubber, aluminium, or the same? Now, this online, this is a difficult thing for me to get a vote on, but think about these answers. Of course, they have the same size, speed, and mass, so in fact, they have exactly the same kinetic energy. But of course, the rubber bullet is deformable, so it will most likely bounce off the block when it hits it, whereas the aluminium bullet will most likely embed itself in the block and stop dead. That means that if we look at the answer to number 2, what will happen is that the damage to the block is most likely to occur with the aluminium bullet. Why? Because the kinetic energy of the bullet will immediately be transferred to the wood and then cause some thermal or other effect. Now, what about knocking the block over? To knock something over, we need to exert a force, and a force is a change in momentum. Of course, both the rubber and aluminium bullet have, say, momentum mv when they approach the block, but only the rubber bullet bounces off and reverses direction. If it's a perfectly elastic collision, it will reverse and have momentum minus mv. So it will actually impart twice the momentum that the aluminium bullet does. So in fact, if you want to knock the block over, a rubber bullet is what you might need. So this is maybe a little bit counterintuitive, but if you have even equal momenta, the impulse is different. So aluminium energy transfer and rubber bullets might be different. So that's what you really need if you want to understand classical mechanics. What has that got to do with anything to do with light? Well, in 1960, when Theodore Maiman invented the laser, most people were doing studies on using lasers for things like nonlinear optics and so forth. But Arthur Ashkin and Gordon looked at this equation where they said, if I shine light on a mirror, what is the force? Now, this is something you may or may not have ever thought about. But you can see here in this equation, if I have a number of photons per unit time n dot, I have the de Broglie wavelength and momentum, h over lambda, I have a power p. The force, which is a rate of change of momentum, is simply 2p over c. So if I have a 1 milliwatt laser pointer and you go home and you point it at a mirror, please do anything like that safely, you will see that we have 2 times 1 milliwatt divided by 3 times 10 to the 8. So that will be 6.7 times 10 to the minus 12, or if you like, a piconewton. So milliwatts of laser power will give me piconewtons of force. A piconewton is 10 to the minus 12 of a newton. It is the gravitational force of attraction between you and your computer screen or tablet. So there's nothing to worry about. But Ashkin and Gordon realized if we could make the objects mass small, as you see, of course, from the equation in the bottom right, what we can do is get large accelerations. And so though this force is minuscule, it is extremely important when we make the object very, very small, which is what we would do in the case of a cell or something smaller. So how do we understand this? Well, what we can do is we can start thinking about how this can hold an object very simply. So here, in this video, you will see an example of a laser beam holding a droplet. This is very simple. So you take a little spray of droplets, like from some sanitizer spray or air spray or perfume spray or something, and you let the droplets come down, as you can see on the right, and the laser beam goes up, and every so often something stops. It's a very nice experiment to do, obviously safely, and you can see there there's many droplets and something gets kicked out. And this is analogously just like the student in America from my collaborator, Brian, who's levitating, if you like, a football with water. But the idea here is, of course, they're not exactly the same because the football on the left is not transparent, whereas a droplet on the right is transparent to light. And this works because this stream of light going up can actually hold a droplet that is coming down. So the beautiful thing is, that is, if you like, a simple demonstration of levitation. The size scale we work at is the blood cell or smaller, so something like 10 microns or so and smaller. Tweezers can go up to around 100 microns in size, but smaller than that is very difficult. To convert this to a trap, Arthur Ashkin, in this paper in Physical Review Letters in 1970, used 2 traps coming in this direction, which was then made into a fiber trap version, as you see here. And this video is from Monica Rich-Marta's group in Innsbruck. And here you see 2 optical fibers, just like my levitation trap. Instead of going up, we're now going sideways. And you can see we can hold objects in the middle. And those of you who can see the video clearly will see the single mode core. There are no lenses. It's incredibly simple, this idea. So it's like 2 jets of light coming from the left and the right and holding a small object in the middle and moving it around. This is very interesting, and I won't have time to talk about this today, but a very rich area of study. Again, the light here, just like the droplet, scatters off it, just like the water, but it also goes through the object, which is really the refraction. So Arthur Ashkin then took 16 years, but he made a very key observation, because instead of just the scattering, we need to think about the light going through the object. And here we invoke one further law from Newton, which is his third law in a simple way. Every action has a reaction. And here, as you can see, we have an object, which is a ball, and we have two rays of light. As you can see, I've drawn the two rays to be unequal. The top ray is a lot thicker and much higher intensity than the bottom, and I ignore scattering to make things easy for the diagram. As you can see, both rays are bent by the ball, but as you can tell, the ball essentially makes more light go down than up. Is this allowed? Yes, that is fine. But because we have created an inequality in the momentum of the light going vertically up and down, material property of the structure. So instead of using a simple dielectric bead, we'll use something a little more exotic, and I'll show you why that's interesting. Very quickly, as many of you know, this won half the Nobel Prize in 2018 for Arthur Ashkin, who shared it as a groundbreaking invention in laser physics. It's long overdue. It's many beautiful examples of physics it can do. Just very briefly, the physics comes from the fact it is an elegant Hookean spring, and this is an idea. The trapped particle oscillates in the trap rather like a spring, and it obeys a Hookean law. And we can, with the particle detector, work out the position of the particle very, very accurately, and therefore make beautiful force measurements, because we can calibrate and know kappa, and we know the displacement, so we can know the force very, very well. This has been used to resolve many things in traps. Here's an example. All of our cells have kinesin, and this moves cargo inside our cells. This is a kinesin motor moving on a microtubule, and this has 8 nanometer steps. Beautiful studies in non-equilibrium thermodynamics, and this step motion here has been resolved by not trapping the molecule, but trapping the cargo. So we trap a bead, and we use biotin streptavidin to make a connection with that. So that's what can be done. You can also do beautiful studies with DNA. Here's a study from Stephen Block's lab in the USA, showing that a single piece of DNA can be tied in a knot. So here we go, it's tied in a knot with the beads, the bright glowing parts at the end of the line are the spheres, and here he's looking at something called enzymology to look at DNA knotting in detail to cause cancer cells to apoptose. That's a topic for another day. What we want to do though is we're going to use some properties of light in a moment, and we're going to use them in vacuum. So what we're going to do is look at what we call the spin and angular momentum of light. And so we know that light is a transverse electromagnetic wave, and if the light is circularly polarized, what we find is that it follows a trajectory as you see in the bottom left. And we know from quantum mechanics, this actually results in a spin angular momentum of the light of plus or minus h bar. This is fantastic and interesting. Light has another type of angular momentum as well. This is not due to the spin or the polarization, but to the phase front. So if you've walked down a staircase like that, you will know what I'm talking about. And these beams are known as Gauss-Laguerre beams, or there are other beams as well that have this angular momentum, but this is due to the inclined wavefront. You see the yellow surface is like a helical structure. So the pointing vector does not go in a straight line, it spirals around the axis. And that means that there's an azimuthal component. This is another type of angular momentum one can look at. A long time ago, Beth wanted to actually study these angular momentum, and he started with spin because orbital was not understood then. And in discussions with Einstein, he wanted to do this experiment where he spun a wave plate in and actually looked at this angular momentum. As you can see, the experiment there on the top right, and this experiment was a tour de force by using a refracting slab because he did not have access to wave plates. And this slab rotated around a fiber, and this exchanged 2 h bar per photon with the plate. A very small number, I hope you agree, and a very hard experiment indeed to do, but he managed to do it. But the beautiful thing is we can transfer this angular momentum to particles, and indeed we can do this in vacuum. So the spin is what we will talk about today. The orbital, like around the spiral staircase, is on the right, and that color is the phase, but that's a topic for another time. Let me show you what you can do in tweezers with this. So what you can do with spinning is you can actually spin with angular momentum. But to do this, we need our wave plate inside the sample chamber. We don't have wave plates, so what we do is we use little birefringent spheres called vaterite, and here you can see these experiments occurring. This is a liquid crystal droplet that is spinning. The one in the middle is a little crystal of vaterite, and it acts like a microscopic wave plate. So the light going through changes polarization, and it causes a rotation. This rotation reaches a terminal angular velocity because what happens is we have a Stokes drag in the liquid, and this can be equated with the equations I'm showing to show you that we can actually get the viscosity of the sample very accurately. So people use this for the viscosity of the sample, which is denoted by the parameter mu. So we know the power and the change in polarization of the light, delta phi, we can do that. You can even do orbital studies. This is just very quickly a video to show that. This is both spinning around the axis you just saw and the orbital around the spiral staircase that you saw from work we did before. But this is also something that can be used. Now, why would we want to do this in vacuum rather than in liquid, where we can do cell studies and also these beautiful studies of viscosity? Vacuum is very exciting because we can make very nice microspheres that are untethered. The beautiful thing about tweezers is the particle does not touch the surroundings, so it is not touching anything, so it's little dissipation. This means the quality factor, the Q factor, is extremely high. So the force sensitivity, F, goes as 1 over the root of Q, so it can be extremely high. I won't have time today, but in about 2 weeks, we have a major paper showing we can exceed 10 to the 8 in this area. And technically, the record will be 10 to the 12. To date, they have seen about 10 to the 6. Also, we could get to the quantum ground state. And this is very exciting because, as you see in the figure in the bottom right, that when you have optomechanical systems, when you cool them down, what happens is the temperature goes down with this oscillation, and we get ground state occupancy. But the problem is this quality factor here actually drops as the system gets smaller. Do you see this pink area? This means that trapped particles disobey this general trend, and you can get very small volume with very high Q value, which is seen in this paper here by Lucas Novotny as well. Believe it or not, one group in Vienna has just achieved the ground state for the very first time in this system, and this is here it is, and they managed to get the occupancy down to about 0.7. I'm pleased to explain that at the end of my talk if anybody's interested, but for time I will skip it. But this is the system here. I won't go into the details because of time, but they have a beautiful cavity cooling thing by holding the particle, and they're looking at Stokes, anti-Stokes scattering, and they get a ground state occupancy here by suppressing the anti-Stokes scattering and a coherence time. So this is the first time an object the size of a cell is really levitated and taken to a ground state with a coherence time of about 7 microseconds. Now, rotation, as we saw, is very interesting and is already used in vacuum. Why is it useful? Here is a picture of somebody on the International Space Station spinning a ball. And as you see, the ball is going through and is making a pass. Now, if you play this game of American football or rugby, you know that you need to spin the ball to give it stability. Angular momentum gives stability to objects. Here we see a little gyroscope or a satellite. So this means angular momentum through spin has something very, very special going on. So to do this, what we did was we used this idea of this special sphere, and we spun it in vacuum. Instead of using a normal object, we levitated the object in a little vacuum chamber, we passed the light through, and the object started spinning. Now you'll remember that in my previous slide, I showed you that the particle reaches a terminal angular velocity because of the Stokes drag, because of the liquid. But here, we don't have any liquid. We only have air. So what we did was we did this experiment, and then we sucked the air out of the chamber. So there's the vacuum chamber. It's a very simple experiment. You levitate the particle, you spin it, and then you suck the air out. What happens? Well, the particle also has a frequency shift because of the angular momentum and ultimately energy exchange with the system. But the beautiful thing was, what happens is that here viscosity becomes a function of pressure. So the red line on the right shows you that what happens because the particle diameter becomes comparable to the mean free path. So on the right, you see that here the particle rotation stays the same because the viscosity stays the same. But once the mean free path goes down, the rotation rate goes up and it goes into a different regime. And here we got rotation rates of up to 10 million times a second. And at the time, this was the fastest man-made object ever recorded. And this is now being used for some beautiful studies and in vacuum and in actually looking for forces. Let me give you one example, which ourselves and some other groups are looking at, is does the vacuum have friction? So if you know about the Casimir effect, when two plates in vacuum can have an attraction, if the plates actually are sheared, like you see in the top left, quantum fluctuations have induced charges. These have a force of attraction, and this can lead to a drag on the friction coefficient. So that's something one can study. And that's beautiful, and we've started to study this by actually not loading one particle, but two. And so we don't have a surface. We look at the rotation of two particles here in vacuum. There they are loaded, and we see when they are spinning whether one particle can sense or understand the presence of another particle in the system. I believe I'm running out of time, so I'm not going to dwell too much on the details of this experiment. I'm just going to show you that we have done some new, I'm just going to skip to the end. What we've done with that system is actually measured a coupling, and then that's in the previous slides. But I think because the time is running out in this talk, I hope that I have shown you, I will stop there, and I hope that I've shown you that optical trapping in vacuum is a very exciting and innovative technology. It has been around for 50 years and made exceptional advances in biology, medicine, chemistry, and now it is making some of the world's most exquisite sensors with levitation, and also challenging our understanding of the classical and quantum interface. These are the people who did the work, particularly Yoshi Arita, Graham Bruce, Paloma Rodriguez Sevilla, and my collaborators below on the theory. And I would also like to mention we have many new postdoctoral positions in our group coming up with an advert soon, and if you're interested, please drop me a line or get in contact. So I will stop there and thank you all for your kind attention.
Thank you, Professor Dholakia, for this wonderful and very informative talk about the optical tweezers and optical trapping in vacuum. We have a couple of questions actually from the YouTube live link, as well as who are there already in the Google Meet. So let me ask those questions on the behalf of those people. So Mr. Karthik Goyal, he has a question. While talking about the manipulation of light, is there any live experiment to understand the concept of recycling of light?
If there is
any live experiment or any experiment is conducted to understand the concept of recycling of light?
Okay, I'm not sure what I understand by recycling. What he means by that, but these were experiments to show the transfer of linear and angular momentum of light. Is that what he means?
I believe so. Any experiment to understand the concept, that's what he meant. So yeah, to recycle the light.
So the experiments I've shown prove that the light has momentum, both linear and angular momentum, and the light energy also changes when the body is set into motion, and you can see that by the frequency of light, the energy of the photon can change. So I didn't have time to explain all of those details, but using that you can measure that.
So there is another question from Parth Panchal. So he's asking what are the applications of optical levitation?
Levitation.
Yeah.
Okay, so what we can do is people can measure, so what one can do is understand, so if I just hold my coffee cup, if we can make it in a quantum ground state, we can understand wave function collapse. If it has a coherence time, in wave function collapse, we can understand if gravity can collapse the wave function. So let's say I levitate the particle and I drop it, the wave, it will give me a time over which gravity destroys the quantum mechanics of the system. This is a very fundamental question. When I put up the Q value, we can make beautiful sensors. So if you have a very high Q, you can measure, in fact, high-frequency gravitational waves, you can measure spin charges, you can measure gravity, you can measure the changes in the tides. There's a gravitational sense that's even more accurate than anything we have because of the high Q value. So these are some examples why people are excited by this system.
Then another question we have from Krishna Kumar. He is asking that what kind of forces light exerts over particles in optical levitation or optical levitation. What kind of forces light exerts on the particle in optical levitation?
Right, so levitation is just like the little drops of water I showed at the beginning. So the scattering force can levitate it, and this gradient or the bending force keeps the particle inside the laser beam. So a gradient force and a scattering force. Also, there will be a little bit of absorption of light. So there'll be a little bit of heating, but usually we pick the laser wavelength and the particle property to keep the absorption very, very low. So those are the main forces that you will, and the effects you will see.
Now, if anyone has question on the Google Meet, you can.
There is one question from Bharat Savarish. Can optical tweezer trap any biological sample?
Okay, that's an excellent question. So optical tweezers, if you remember my equation, it has the parameter polarizability and gradient of the field. So if I trap, let's say we can't trap objects that are typically bigger than around 100 microns because they are too big and the forces are too weak. At the size of a cell, if the light can be bent and refracted, yes, it can trap. If it gets too small, the polarizability of the object is very hard. So to directly trap a molecule is very difficult because the polarizability is small and I cannot create a big gradient. So trapping cells, very easy. But you can overcome the idea of this gradient by using near-field traps. So people that may know about plasmonic tweezers or other near-field traps with big delta I. You make the field gradient strong, you can trap maybe a virus or even a protein, but this is challenging. So mostly people trap cells, or they take a bead and they make the molecule is attached to this and they watch the bead motion like the kinesin to do things.
One last question from Krishna Kumar. What is the probable lowest limit and highest limit of vibrational frequencies experienced by the trapped nano-dimensional structures?
Right, so the trap frequency, this frequency in the trap, typically in the vacuum traps, the highest we would get would be maybe something like tens of kilohertz at the moment, and the lowest would be sort of tens to hundreds of hertz. So we would like a high frequency because in the levitation, because mean N, remember the occupancy, it goes as kT over h bar omega. So if we have a high frequency, the occupancy comes down. So this is the problem that we would like to address with stiffer and better trap design.
Okay, yeah, we have more and more questions coming, certainly on the, but I think we can end here, owing to the time constraints. But thank you very much for this really informative talk, and certainly lot of things that people were keen to know in the optical tweezers. This is one of the very recent and advanced area. So again, thank you very much, Professor Dholakia, and thank you again for taking out some time, even being in Australia. Thank you.
Yes. Thank you so much, and I wish you all a continued success and enjoy the rest of this very exciting meeting. Thank you for the opportunity.
Thank you. Thank you.
Thank you.
With that, we would like to move to the next speaker. I'm going to share the screen here.
Yeah, Professor Brian is already there. I can see.
Yeah, he has already joined. So I hope you can see the screen. Our next speaker, we have Professor Brian Culshaw. He is, I think, let me just check that he can hear us. And Professor
Brian, your mic is mute. So you please unmute your microphone, which so that we
Turn the microphone.
Okay,
Yeah.
now we can.
Is that better?
Yeah, now we can hear you. Thank
You can hear me now.
Yeah, thank you. So yeah, thank you and welcome here in this event. So our next speaker, Professor Brian Culshaw, he is a Professor Emeritus at the University of Strathclyde in Glasgow, United Kingdom. Very briefly about Professor Culshaw, he did his PhD from University College London in 1969, and he worked as a postdoc at Cornell and at the Bell Northern Research Lab. He moved to Strathclyde University in Glasgow in 1983 as the Professor of Optoelectronics, and since then he has also been involved in a number of professional activities, including multi-partner national and international research project management, conference organizations, and journal editing. He has also served as the President of SPIE in 2007 at Strathclyde. He has served as the Vice Dean Engineering in the UK's largest engineering faculty for 6 years, and also he has been the head of the department for 5 years. So I would request Professor, he is going to speak today about the photonics, what is it and where might it lead. I would request Professor Culshaw to kindly share his computer screen, and please begin the talk.
Okay, here we go. Is this working? No. Present now. Let's have a window. Your entire screen. There we go.
Yeah.
And hopefully this will work.
We can't see the screen, sir.
Now, is that working? Do you have a...
We can't see the your shared computer screen. We can only see your face.
Right. So do you have the presentation, the beginning of the presentation?
No, not at this moment.
No. Oh, okay. Let me go back.
Right in the corner there is a present now link. You have to click over there.
Yeah, I'm just looking for it.
In the corner
Share your entire screen. It says here, so I'll share. Now where's the thing gone? Sorry about this, folks. I am certainly not, as you can see, not expert at this.
Also click on the screen. There is a screen coming up. After you click present now, there is a screen coming up, so you have to click on the screen as well.
Okay, I've got a dear. Sorry about this, folks. We managed to get it to work yesterday, but now do you see the presentation now?
Not at this moment. If you just go to the corner of your this computer window, and if you place the cursor somewhere, a small
three dots. There we go.
pop up, and present now is written there. And once you click that.
Oh dear, just a moment. Here we are. Present now. Got it. A window, your entire screen. Now is that doing something?
Once you see that entire screen, then you have to just select that screen over there, and then it will then click the share
Is that
button.
it? Now, is that working?
No, not yet. Well,
It is working.
Hello, Brian, this is Arup here at this end. Can I help
Hello.
you?
Oh, I'm sure you can.
Yeah, so the organizers, if I may take the liberty, Brian was my PhD advisor, so I'd like to help him in return for all his help.
yeah, please go ahead.
Yeah, so Brian, on the right-hand side, do you see turn on captions and present now?
Not at the moment, just a moment.
If
On the
you
right-hand
hover
side.
your mouse button towards the right bottom of your screen, there should be a present now button.
Oh dear. Now, where are you? It's not appearing on my screen at the moment. Just a minute. Share, cancel.
You will have to
Here we
move-
go. Now I've got present now, yeah.
Right, so if you can click on that, please.
Yeah, I've got it.
And then you should be seeing another window with yourself within it.
See
You
the
should be
screen
seeing
with me in
yourself,
it.
yeah? So you need
I don't
to click on that screen within that.
Click on the screen with myself in it.
Yes, yes.
I can't find. Oh yeah, there we go. Got you.
Yes.
Yes.
And now, yes, and now that blue share button has come alive.
It has.
Could you please
There
click
we
that?
go. I'll click that and I now present.
Yes.
And if I do that, share. Now, does this work? Have we got a title?
Not yet. Not yet.
Oh dear. I do apologize, people. I do apologize. Thank you for your help, Arab. I'm still... I've got the blue types, the three. There we go. Come on, you. Oh.
So,
Three tags there. No, that's wrong. Three tags. Oh, I'm very sorry, folks. Very sorry. This is crazy.
Brian, can you see the screen?
Yes.
I can see which screen? I can see a tiny picture of me.
On your computer.
I can see Ranjan, is it? I can see a picture of Arab.
Yeah, so try to pause it. So here,
We got this going.
like this. So that small screen comes like this, and you have to share in one of them, just like this. Share.
I haven't got the share screen lighting up like that.
Oh yes, it's coming now, hopefully.
No, that is mine.
Yes,
That is-
oh, it's yours.
This is my screen. I was just trying to demonstrate.
Oh, my apologies. I've never, as you can see, I've never done this before. Life is full of new experiences. So, let me try this present now one again, which is here. If I present my entire screen, yes, not just the window.
Yes.
Chrome wants to share the contents, so you choose what you'd like to share. Oh, I see. There we go. Now I think we have it. With a bit of luck. Is this? Let's try this one. Now, do you have a presentation now?
Yes, now it is coming. Yes.
Yes, yeah.
Is that working?
Yes, it's working, it's coming, yeah. Thank you.
Oh, brilliant. Thank you all for your help on that one. We'll see if we can get going. As I say, my apologies for the hesitant start there, but it's all working now. So this should have a new slide, yeah? You have a new slide? Okay, well, let's try this. And so, we've all seen all these things about photonics.
and there's a whole bunch of things going on. And as you know, today is the International Day of Light, following on from the Year of Light in 2015, and this was taken from the International Year of Light website, and I kind of thought it was a nice picture because it just shows the various places in which light can be helpful. They defined light on the International Year of Light website, and this is what it said: the science of light, the technology of generating, controlling, and detecting light waves and photons. These are particles of light. Photonics underpins technologies of daily life, from smartphones to laptops to the internet, to medical instruments to lighting technology. Just a moment, get myself onto this, there we go. And the 21st century will depend on photonics, as the 20th century depended on electronics. Now, that may sound very optimistic, but I think there's an awful lot of truth in it. So what we're doing here is going to talk a little bit about photons and when do we need to worry about these things. Well, this is repeating. The photonics is the science of light, etc., etc. Controlling, detecting light waves and photons. Well, we kind of can imagine waves and rays because we can sketch them and see them. We can imagine electromagnetic waves, electric currents, because we can kind of draw little pictures. But we're a little bit uncertain as to photons, because in principle, the photon idea applies entirely across the electromagnetic spectrum. So here's an attempt to answer when photons become important. If we look at the electromagnetic spectrum, well, as we can see there, we use most of it. Radio waves, microwaves, etc., etc. And visible is just this tiny little bit slightly to the right of the middle there. Why does this photonics appear? Trying to quantify this, I did this sketch some years ago, but the basic thought is that, well, you've got thermal agitation of various bits in your, basically in the atmosphere, in anything, there's always thermal agitation. And if you look at particle energy, depends on temperature. So the dotted line across there is the particle energy at 300 K, and the blue line is the photon energy as a function of wavelength of electromagnetic radiation in meters. So you see where the two cross and where photons come. And the visible spectrum, it starts at about a little bit more than 1 electron volt. If you do 1.24 over lambda, which is much easier to remember than the other way, that gives you the photon energy in electron volts. Of course, if you go cold to 3 Kelvin, then you're starting to look in the microwave region of photons, and a few people have played around with microwave photons, but it's a little bit esoteric. So there we go. What is a photonic system? Well, you generate the light as photons, as you do with any electromagnetic radiation, but often you don't worry about that. And there's a whole bunch of ways of generating light. And then you have to play with them, because if you don't do something with them, then there's really no virtue in the light, if you see what I mean. Even if it's just looking at the scene outside your window, you have, in effect, manipulated some photons by receiving them on your eye and all this kind of stuff. So they can vary in space, they can vary in time, you can have intensity, wavelength, polarization, a whole bunch of things you can play with. And then you transmit them. And they can either go as waves, which is the usual way of thinking about them. Sometimes you have to think about them as going as particles, but often that's a little bit tricky. And sometimes they go as electric currents. They've been called plasmonics, but that's essentially what they are, electric currents. And they're transmitted, as it says here, free space, things are a lot bigger than wavelengths, so they're in waves. Waveguides are about the size of the wavelength, and nanostructures, you get currents and synthetic dielectrics and a whole bunch of other things. Synthetic dielectrics, sometimes called metamaterials. And then you've got to detect them and then work out what the information was that you put on in the first place. So that is a photonic system. So what do you need to know about to work with all this? And that's the kind of question we're trying to address here. Well, this is a map of photonics. I'm certainly not going to go through all of this today, but you get the general idea. You are looking really at the behavior of light in materials and structures, and you can categorize that as propagation studies and as interactions with materials. And there's quite a lot involved in that, as you can tell from just the headlines there. I say I'm not going to go through that in gory detail at the moment. Also lots of applications, as we've already hinted, and this just keeps on going and going and going, and it's growing by the minute. So if you look at light, well, how do photons behave with materials, in materials with structures? And this is just touching at it, a very brief look. In the material itself, you have spectroscopy and materials responses. You have propagation characteristics in features large compared to lambda, features comparable to lambda, and structures much smaller than the wavelength, where a bunch of other interesting things start to happen. So how does light interact with materials? Well, if the electron is bound to the atom, then the electromagnetic wave basically shakes the electron around the atom. That's one way of looking at it anyway. And it works very well. There's a Clausius-Mazzotti relationship, which is behind all this lot. And you eventually look at just a basic mass spring damper relationship between the motion of the atom, the motion of the electron, and the electric field which is applied. And there are ways you can put numbers into all these constants. And there's a generic behavior for resonant frequency systems, which you're probably all very, very familiar with. And it's it's there. You have a displacement which peaks at a resonant frequency and phases off to zero at high frequencies, and do have a phase switch during the displacement. And that generic thing works quite well. Even for molecules, and this is just a very simple molecule, and indicating a whole bunch of possible resonances which can occur within that simple molecule. So there's lots of resonances going on, and there's a generic response which basically looks like this. You have the real part of the dielectric constant there on the green curve, and at the bottom you've got the losses. The losses will give you the color or whatever it is you're looking at, and the resonances. When you go through every resonance, you drop the index. What is interesting, and is a discussion topic in its own right, is you can, towards the UV, often get a refractive index which is negative, which means surely that light must go faster than light. And I don't think that's allowed. And in fact, when you look at it carefully enough, it doesn't quite work out that way. But we'll worry about that some other time. But this signature is unique to every single atom and every single molecule, and you can identify what you've got through this signature. And there's some more general comments that you can make, some simple observations. The more molecules you have per unit volume, well, the higher the dielectric constant. And if you have more molecules stacked in one direction than in another direction, then you have anisotropic materials, and also the photoelastic effect and quite a number of other things. Suppose the material hasn't got electrons attached to it, but ones that are free to roam, like in metals, for example. Well, in that case, when you apply a field, the electrons go one way, the positive ions go the other way, but they don't go very far because they're a lot heavier than the electrons. So they tend to stay still, give or take a bit. And so what you've got is, again, a mass spring damper. The damper is the collisions between the electron motion and the particles in the material. You have, as we said, the mass is the electronic mass, the restoring force is the electrostatic charges, and the losses are the collisions. It's a plasma. Now, if your excitation frequency goes above the collision time, or the inverse of the collision time, which is what I meant to say there, then suddenly your metal becomes transparent. And this is very familiar, of course, but sounds a bit strange when you first think about it. So the losses go to zero because they're, well, not zero, but effectively very much less, because the collisions aren't given the chance to occur. Now, it's interesting because you're at very high frequencies, basically, when you've got the plasma frequency, where, you know, it's, well, really, shouldn't you think about photons? But in this context, it's much, much simpler and straightforward, and it works to think of it in terms of classical electrodynamics. Very strange. Of course, the metal thing is interesting as well, because if you look at skin depths in materials, and this is a rough calculation, the vertical scale is either skin depth in nanometers for the curves going up the way from left to right, or it's the resistance of a gold wire for the one skin depth in diameter, 1/10 of a wavelength long. And what you see with this gold, of course, if you're looking at 1,000 microns a millimeter, then the gold wire has a resistance of an ohm or two. Whereas if you go up into the optical region, this gold wire has a resistance of hundreds of ohms. And there are some rough and ready parts of this, I admit. But the essence of it is that if you have lots of metal around, then things are very lossy at optical frequencies, until you get to the blobby region on the left at the bottom there, which is where you have the plasma resonance. That said, it is quite possible, if you get less than the skin depth in the metal layer, you do get electric currents flowing. And the whole of nanophotonics is essentially that. basically make the metal thin enough so it doesn't become very lossy. But you have to account for this strange skin depth. If you go into non-linear properties of materials, then you've got Stokes and anti-Stokes and the usual things. And we tend to go into energy levels for this because this is convenient. Though you can actually treat the whole thing in classical terms with non-linear oscillators and a bunch of other things. But this is the one that people tend to use. And what I'm trying to say here is that the way you view photonics depends on what you want to do. Structures, well, there's the simplest structure. You can have a plane interface, and that's all well known enough. And there's the low to high and the critical angle and all the usual kind of stuff. And we can, of course, do things with lenses. And it's amazing what you can do with this simple index of refraction relationship. All these very complicated lenses that appear on the front of fancy cameras and satellite imaging systems and whatnot, they're all put together with ray optics. And again, why? Because it's convenient to do it that way. So there we go. And when you get to the dimension around the wavelength, you have diffraction, interference, scatter, and the ilk, and you have the effect of defects and scratches, and you have the impact of waveguides and so on. And there's a whole bunch of things you can do, and you have to think about the structure as essentially an interference structure of some form or another. And there's the simplest interference thing, or one of the simplest, the old young slits. And again, we can talk for hours on this, but the basic ideas all remain the same. And if you get very small, then you start to mess around with the energy levels. Now, here we're looking at the structure in a different fashion. We're looking at energy levels and the impact of the dimensions on Schrödinger's equation, in effect. Though the colors of colloidal gold have been around for centuries and used in pottery for centuries, I suspect there's some Indian museums with some samples around. In fact, I'm pretty sure there are. So there we have that one as again, a different way of looking at solving an optical problem. So what about all this photons, waves, and current stuff? Well, is light a wave, a particle, an electric current? And the answer is, yeah, depends what you're thinking about. And you could always use an inconvenient model if you're perverse enough. But you always try to find, at least I'm probably quite lazy, but I would inevitably try to find the simplest way of treating the issue. So the basic thing is they're created and detected as particles, as indeed is the entire electromagnetic spectrum, but at lower frequencies you don't worry about it because there's so many of them that they don't matter. You can transfer them as waves or electric currents, plasmonics, but in optics, plasmonics doesn't go very far. And there's a few exceptions around, and I say we'll ignore those for now because it's another way of looking at things, and this is one of them. I haven't talked too much about entangled photons. If you really are into an interest in this, I have actually read Jonathan Dowling's book. It's about 400 pages long. There's not a single equation in it, but you have to think, at least I had to think while going through it, but it's very enlightening. So that's photonics in a nutshell. What about applying it? Well, and what about a future? Because I don't know what the audience looks like here, but I'm guessing there's a few students and young folks around. At least I hope there are. It's really about this. The International Year of Light statement that the 21st century will depend as much on photonics as the 20th century, depending on electronics. And if you think about how disciplines evolve, well, research is the beginning. Perhaps there's something useful. If there is, maybe there's a product. That typically takes a couple of decades or so. And there's all sorts of interesting contributions you can make at all phases can be. So you can probably sketch it as a map. So you go basic to applied, to product development, to manufacture, to accreditation, commercialization, and marketing. And you see the arrows do doubles ended in that little lot there, because everything is interactive in there. Porter's 5 forces, which I haven't mentioned too much at all before, but if you look that up on the web, you'll find an interesting account of this. So there's your lab demonstration in a field trial. We did a field trial in a field, which is why that picture's there. It's all to do on this particular occasion with methane detection. So the user compares with competing technologies. And the canary is there because canaries were used in underground mines in a major mining country, which wasn't India, by the way, until about 2007, I believe, because they knew they worked, or when they died, they didn't work. If the user's convinced the new idea is good, if he's not convinced, then you just go back to the start, and that gets you into familiar territory. But if your user is convinced, then you have a whole bunch of other things to think about. And they're actually quite interesting too. You don't write quite so many papers about them, but if you're in the standards game, you write a lot of standards, for example, and you have to communicate among all these people. And there's where your 2 decades goes. And this is a quick example, the fiber optic gyro. There's a classical gyro on the top right, spinning wheels, and it is very, very difficult to make if you want any decent performance from it. The fiber gyro is interesting because it has no moving parts, and that's a very early one. Here's the first. The plane that the first one was in, the Boeing 777, about 94, and you can see this part of the 20-year gap there. And now there's some rather nice ones around. This one will detect 1 rotation in 100 years, which is pretty sensitive. And this one will fit, not just in your pocket, it'll fit in your wallet. So there's quite a few fiber optic based systems around now. And one of your possible career paths is to participate in this because it's quite entertaining. And where can you use photonics then? Well, we've looked at all this, and you can read through all this lot, but we'll come back to them anyway in one way or another. You'll often still need to persuade someone that photonics is a good idea, even now, because the word hasn't crept into the vocabulary quite yet, like electronics has. What might trigger the new product idea? Well, there's all sorts of things you have to you have to manipulate the light, and there's a whole bunch of optics around that you can play with, and you've discussed some of this already. I don't really, again, can talk for an hour or two on each of these. But here's the sort of things that are coming into the toolbox, you see. You have silicon integrated circuits. And there's featured on this month's Nature Photonics. I haven't read the article yet since I only got it yesterday. But there you go, silicon ICs. Super resolution. Well, this is basically nothing more than an oscilloscope probe, isn't it? Basically, but it's a super resolution image detection system. There's nanophotonics. There's an LC resonator. Look at the dimensions there. It's not very big. Or you can make a Yagi antenna like that one. It's a bit like your TV aerial up on your roof or wherever you have it. And there's even been an odd transistor coming up basically based on graphene and H-boron nitride. So there's quite a few tools around to do really quite intriguing things with. So that's the tools to play with. What does society actually need? Well, in the last few months, Photonics-21 did its latest strategic roadmap. Photonics-21 is an EU organization, and they identified all this lot as places where photonics can make an impact. And there's as you can see, there's 80 pages, 90 pages of text on that, and you can read it because, but the net conclusion of it is lots of sectors, lots of opportunities. Photonics in Europe is currently worth about 60 billion euros a year and is growing at just over 6%. That was written before this coronavirus thing, but it'll continue and settle back again. And there's probably similar reports in India as well. There certainly is a National Photonics Initiative in the US. And you've got another lecture just coming after this on probably that particular topic. And there's the free download from Photonics 21, and you can just twig onto it and off you go. So, a lot to be done. Lot more around, and lots of opportunities and optimism and opportunity. And what about young researchers and students and so on? Well, what do? You've got your electronics of the 21st century, and it'll go into all kinds of areas, and we've hinted at several of these already. How do you get the best out of it when you're a young person? Well, you can plan it or not. Too much planning can get oppressive, so I kind of feel it's unrealistic. Just keep an eye open for your lucky break, and look for you might look around for an interesting opportunity, and follow your instincts and interests. And generically, yeah, the research is interesting. There's no denying that, and it's fun. But if you want to make an impact, you've got to make something that actually does something useful. Personal opinion, but that's my personal opinion. Making this impact needs teams of different people doing different things, and you've got to communicate among all these people. And you also got to be patient, because the time spans are far from instantaneous. And a lot of people find it's fun doing that as well, and we have lots of students who are in this particular domain at the moment and enjoying themselves tremendously, or former students. But the most important thing to do of the lot is enjoy it. And that is critical, because if you enjoy it, you go home to the family in the evening in a good humor, and with a smile on your face. And that's probably the secret of the ideal career. So, thank you all for listening. Thank you.
Thank you very much, Professor Kalshaw, for this very informative basic general talk on photonics. I think it is really much appreciated by very young people who have joined us through the YouTube live streaming. They have a lot of questions here, very basic general questions. I can ask those questions on their behalf. The first question is asked by Parth Panchal. He's asking that can we have, similar to photonics, can we have gravitonics in future?
Itonics?
Gravitonics, gravity related. Gravity.
Oh yeah, okay, looking at gravitons. Now that's well, I guess you probably could. Yes, gravitonics sounds something. I hadn't thought about that one. But I think that what you do with it, you can't really manipulate the, what's the word? The world, the planetary system. though some people might like to say they could, and I would not think of anybody in particular, of course, but they're probably in the United States. No, I've not come across that one, but who knows? So, real answer to that is don't know, but it sounds interesting.
Then there is another similar question. There is another similar question by Shubhanshu Shekhar. He is asking that is there a possibility in future that the whole electronics can be replaced by photonics? If yes, then will it be equally accessible?
I think there's you see, in principle, it already has been, because if you look at it all as electric waves, electromagnetic waves, then really electronics is a branch of photonics. If you're looking at 1 megahertz, and a 1 megahertz electronic circuit is a nanophotonic circuit. So it's a continuum, isn't it? I mean, this is the thing that I found most fascinating over the years, is that when you look at it depending on your perspective, they're not separate disciplines. They're a continuum of disciplines, but you have to take in mind that the materials that you have, the properties of the materials, are actually a function, and often quite a strong function, of the frequency. And in fact, the electronic designers have been looking at that for years. You know, if you go into high frequency, you have to consider the inductance of a straight piece of wire. So it's where do you draw the line? And this is the bit that I actually do find intriguing. It really is not a totally separate discipline. It's just part of a continuum. And many of the ideas apply, if you are careful enough about it, many of the ideas will apply through the spectrum. But you have to be careful, especially with material properties, and especially also with structures. But you know, if we talk about metamaterials, which have had a lot of fuss, well, I remember as a research student making a metamaterial which was designed for 10 gigahertz. Only we called it a filter. So there you go.
Yeah. So another question from Himanshu. He's asking that what are the possible applications of metal nanoparticles in photonics devices?
Metallic nanoparticles?
Yeah,
oh.
In photonics or photonic devices.
Well, they're already used by the biomedical community quite a bit as indicators of, and again, I'm not an expert here, but they are used in quite a number of clinical tests for a number of diseases, blood problems, inflammation, and so on. But I would not claim to be an expert here at all. But they are certainly already in use, the nanoparticles, as clinical enablers for biophotonics. And there are lots of other possibilities, I'm sure. Witness the ancient pottery that has been around for, well, not just centuries, millennia. That's been used nanoparticles.
So yeah, another question is there. So a lot of questions from probably undergrad students. There is another question that you talked about the photon energy versus wavelength. How to have the experimental manifestation? and also how to have the experimental manifestation, and also can we get the same feeling from theoretical computations, and are there good books that you can refer to?
Oh, right, okay. Are there good books? Depends what you want from your book, is the simple answer. There are certainly a lot of specialist texts around in various parts of the photonic business, and I have some of them here. There are whole textbooks dedicated to, is it a photon or a wave? And they are, well, for me it didn't get very far, that one. But I have tried to read it. There are some very good collected graduate level texts around. I have actually just tried to write one as an introductory one. So if you keep your eyes open, look at the Cambridge University Press website, you can have a look at it. You may or may not be interested in it, but that's a very introductory text, and it's a couple of hundred, 150 pages or so, along the lines of the talk that I've just done. Only it's, in fact, it was starting to try those talks that got me into writing the book. But I mean, honestly, it depends what you want to get out of your textbook, and without that being known, it's kind of difficult to answer it.
So well, there are a lot of questions on the YouTube streaming, but I think we can take one or two questions from the Google Meet, the people who are live here. So I think if they can by themselves ask, or Professor Parua can ask on the behalf of them.
There are already some questions. One question is, what are the potential area of photonic research which can have impact in near future?
What are the, sorry again, I missed that a little bit. Aspect.
What are the potential area of photonics which will have impact in the near future?
Which of the bits of photonics will have the most impact? This is one of these. I think the basic answer is I don't know, but I think if you look through things like the Photonics 21 report, which is well worth a read if you're at particularly at the beginning of a career. I think it's well worth having a go at that. As I say, it's free, so you just put Photonics 21 in Google and you'll get it. And what this does is highlight several sectors, and each of the sectors, it gives a discussion on what are in effect viewed to be the important areas for that particular sector, so that you can go through the sectors where you might want to see something happen, and say, well, in order to address this, I will need to get an interest in this particular bit of photonics. It is a very wide-ranging topic at the moment. Where are the interesting areas that happen? I think you will see a lot going on with nanophotonics in its various forms. But as we've mentioned already, that's really integrated circuits for optics. And it's quite an art and science to get them to work, because, as we've also mentioned, you have to take into account a lot of evolution in the properties of materials and the design and the way that structures work as well. But so it's really, I'd recommend go away and read the Photonics 21 report, or look at the National Photonics Institute in the UK, in the US, I mean, National Photonics Initiative, sorry, in the United States. They will also have a story to tell. It's much the same story, by the way. Mild differences in emphasis. But there's a lot of potential in a lot of areas in there which are mentioned, and there's also a section in the report on research sectors which they feel to be the most important.
Yeah, there is another question by Ukesh. The question is, can there be a computer based on photonics?
Well, there sort of already are, and that very, I mean, the Nature Photonics cover, which I showed you, talks about quantum computing and nature and optical photonics and the photonic computing. So they're there. They don't work as well as electronics do yet, but they do exist and have been demonstrated. And if I'd had that article a week ago instead of just yesterday, I'd have had it read by now and be able to make a better judgment on it. But if you look at the May 2020 edition of Nature Photonics, it's right on the button for that one.
Yeah, thank you, Professor. So I think one very good lesson, one very good advice to all us researchers, what Professor Kalshaw said, that when we go back to home from our lab, if we go back to this, I think that is the greatest advice to all of us.
Yes. I would very definitely support that one. Because I've certainly been in both situations. Won't go into detail, but
yeah, thank you very much, Professor Brian Kalshaw. It was really a wonderful talk. A lot of questions are still there, but owing to the time constraint, we have to end this discussion. But it was really informative talk for all of us, and I really appreciate that you came and you delivered the talk, although you are not used to of this new platform of video conferencing. But thank you for and thank you again for delivering the talk.
my pleasure, and thank you for putting up with my naivety, particularly at the beginning there. And I do appreciate it. It's been a joy to talk to you all. I wish you all well for the future. And if you have any questions or queries, then you could always get in touch and I'll try and answer them. But I wish you all well and enjoy the rest of the day of light and basically the rest of life.
Thank you. Thank you very much. Have a safe and healthy day. Yeah, thank you.
Thank you. Yeah. Bye just now.
So now, thank you. Yeah, now we can move to the next speaker. Let me share the screen over here. Professor Dr. Naresh Chand, he is already with us. So let me share the screen for now. And let me just check the connection with Dr. Naresh Chand. You can hear me. I think your mic is muted. So can you please unmute it, Dr. Naresh Chand? Yeah, please can you unmute your mic? We can't hear you. Can you see the option of mic just at the bottom of your screen in the middle? No, we can't hear you. No, we can see that it is muted. So if you can unmute, because we can't unmute it from our side, you have to do it. Okay, yeah.
Can you hear me now?
Okay, now perfect. Thank you. Now
okay,
we
great.
can hear you.
I'm sorry.
Okay, Thank you. So now hopefully my this computer screen is visible to all of you. So our next speaker we have is Dr. Naresh Chand. Let me briefly tell about Dr. Naresh Chand. He is a life fellow of IEEE. He is currently the Associate Vice President, Chapter Relations of IEEE Photonics Society, US. He is also the Associate Editor of Photonics Journal. He is the Chair of North Jersey Chapter of Photonics Society. Formerly, he has served as the Director of US R&D Center, Hawaii Technologies. He was also the Fellow of Engineering and Technology, BAE Systems, US. He has been the Distinguished Member of Technical Staff, Agar Systems, and he has also been in the Bell Laboratories, New Jersey. He has been the Scientific Officer, Department of Electronics, Government of India, New Delhi. So he will be delivering a talk today on photonics opportunities and challenges in India. It's really a pleasure to have Dr. Naresh Chand. He was here with us in December as well, and it's really great to see you back through video conferencing this time. You're welcome, sir, and please if you could share your screen. I'm here stopping my screen.
Thank you, Professor Vikram Kumarji. It is a great pleasure of mine to be with you this morning, this afternoon, early morning. It's 6:30 a.m. here. Could you hear me?
We can hear you, but we cannot see the screen, your computer screen.
Oh, you cannot see the screen?
Yeah.
Oh, just 1 second.
If you take your cursor in the corner, you will see the present now, and if you could share the entire screen.
Just 1 second. I thought you were still sharing this. I think.
No, I have stopped sharing it.
Okay. Could you see now my screen now?
Not yet. Not yet. If you hopefully did you click on the present now? And
Okay. Screen 2, okay.
Okay, it's coming.
Okay. Could you see now?
Perfect. Yes, we can see now.
Okay, so Dr. Kumarji, thank you so much for inviting me. It is my great pleasure and honor to be with you people today. Today is the International Light Day, the 60th anniversary. Today is the day when the operation of the laser was demonstrated. So it is a great day, and by the way, today is an auspicious day for us also. I'm expecting to be the grandfather of our fifth child, a daughter. Could happen today or tomorrow, just waiting. So it's a wonderful day for us. So this morning, my time, or afternoon your time, I'll be sharing some of my thoughts about the photonics opportunities and challenges in India. Last year, I traveled at few places, IIT Bombay, IIT Guwahati, Mangalam Engineering colleges, and met a lot of people. So I was able to gather some information, and I thought that why not I put my thoughts together. So though I am representing the IEEE platform, so whatever I talk today is purely my view and not of IEEE. In IEEE, we all are volunteers. We all are crew in IEEE, so please do not consider my view as IEEE view. I just retired from the the US R&D Center of Huawei, and I have been working with the industry for the last 35 years. And I cannot share anything which belongs to my employers because then I need their clearance. So I'll be making a very generic and high-level talk, and I fully agree with the previous talk. I really enjoyed the previous talk the Professor Kulshos shared. I'll be reinforcing those views. So essentially, we'll be talking about the same thing. The important thing is that the IEEE, the goal of IEEE is in advancing the technology for humanity. Technology by itself means nothing unless it serves a purpose, it serves the society. Also, the Photonic Society is working for transforming science into technology. Again, the science itself has no value unless it serves the humanities, it helps the society. Now, to bring the community in India together, we have taken this initiative. Prakash Bharti, we would be releasing a newsletter today. And if you see in the center, the message in Sanskrit, Tattvam Asi and Jnanam Param Ballam. So this is the summary of all the Eastern system of knowledge. And if you understand this, then this would empower you. So I guess most of you might know the bottom part, Jnanam Param Ballam, the knowledge is all powerful. But the top part, some of you might know it. This is the summary of Indian system of knowledge, but it is practiced in the West. It means I am that. And that is what is important, that what I seek means that means sky is my limit. I am Brahman. I am the solution and I am the problem, I am the solution. So it leaves entire responsibility on you. Your career responsibility is yours, not of any politicians, not of your advisor, supervisor. So it gives the entire power to you. Many times you might think that, how come we in India are not the great achiever, whereas people leaving India and they go abroad, they become very high achiever. Because here when they come, they are given ownership and they are told, hey, your sky is the limit. Come with the solution, not with the problem. So here, I cannot go to, say, my manager, my boss, with a problem. I have to first find a solution before I can go. So this particular slide, it represents, a lot of the information which could be, you should think about it. Just think about it that the tier 1 universities in the US, consider Harvard, Princeton, MIT, Yale, Cornell. If these universities have to admit students based on merit alone, then you may find that 90% of seats will go to Indians, Chinese, South Koreans, Taiwanese, and Singapore and Japan. So you are the best. You are not second to anyone in the world. You are the youth, you are the future. So you have to realize your own strength today. So my first slide, I just want to give an introductory background, though you already know it, but just for, because some of the audience here may not be from the photonics background. So I put this slide, the light travels as a wave, but when it interacts with matter, it behaves like a particle. And the particle is called photon. The optics is to manipulate the light through lenses, mirrors, and photonics is to generate, modulate, and sense and process photons. And if you see that here, when you have to generate photons, you have to modulate them, you have to detect them, you have to process them, you need electronics. So electronics and photonics, they go together. They are not separate. A photon has no mass, but it has a lot of energy. And it travels the speed of light, it can carry a lot of information. And because of this capability, we are able to have this conference today, right? So whatever we are doing today is the information is carried by photons. Today is the key enabling technology of the current fourth industrial revolution. We are at the beginning of that. It plays a vital role in our everyday life and everywhere around us, especially in this COVID-19 environment. You people might not know it, but Wuhan in China, where this COVID-19 originated, it is supposed to be the photonics valley of China. It is equivalent to Silicon Valley. So there are a lot of photonics company in Wuhan. I have spent quite some time. My company, former company, Huawei, they have a big presence in Wuhan. They make the components for the communication systems. So I have spent quite some time there, and because so many people from all over the world go there, and that's how it is spread. So the photon, I guess, is also the reason that we have this COVID-19 everywhere, because people were traveling to Wuhan. Wuhan is a very important city of China, Photonics Valley. So you heard in the previous talk that they have this photonics initiative, strategic planning from 2021 to 2007. In US also, actually most developed countries, whether it's Japan, China, Germany, England, or America, they all have the National Photonics Initiative. In US, the name changed to National Quantum Initiative, because the photonic process is a quantum process. So to provide the solutions to the major social economic challenges. So it's unfortunate that India does not have a National Photonics Initiative. It requires a low carbon footprint. It doesn't require much power, but it offers big opportunities to India to contribute and benefit. India can produce, can consume, and export both products and services. My feeling is that photonics could contribute to 5% of India's desired 5 trillion economy. The important thing is that the photonics is a multidisciplinary science. You don't have to be just working in the photonics. Even the mathematician, statistician, your physics background, mechanical engineering background, chemical engineering background, biological engineering background, all have places here. So because it requires technology from all fields, right? And as you heard in the previous talk, the 21st century will be of photons, like the last century was of electrons. It requires private, public, and foreign investments. You might have seen this slide before. I presented it at IIT Guwahati. In 2018, the photonics global market was $636 billion and is expected to reach 1 trillion by 2024. Okay, and that is about 1% of the global GDP. The growth rate is 8%. Now, at least India should contribute 10% of that, $100 billion, right? India has the 17.5% world population, and Indians are very smart, right? You are the smartest people on earth, right? So there is no reason that India can't contribute 10%, because the good thing is that India has the local market. So the chart here that gives you the breakup of different technologies and their contribution. You see the display has the maximum contribution, because display you use your computers, your TV sets, your cell phone, right? The information technology, the photovoltaics, that is the solar system, solar cells, like production, defense, communication, lighting, optical components. So these are the different areas and the different numbers. So you know where is the money, where is the growth. And at the beginning of your career, you have to really decide which area you want to be, because right now you must know that there is a tremendous unemployment overseas. In US today, 25% of the working population is unemployed. And similar thing is there in Europe. So for you, getting out of India for employment would be a big challenge. So you really have to focus on where you can contribute in India. So here I listed some areas, here 14 areas. And whatever you do, you have to think about which area do you belong to. Because if you require funding, you have to justify why are you doing it, what problem you are solving, right? So the very first thing, you may think that it is not a scientific problem, the photosynthesis to clean air and beautifying our surroundings. This is the most important thing in India, right? We have so much pollution in all major cities. You can't breathe. And so this is the most important. This is the success story of India, the energy. Indian government, they want to have 100 gigawatt power installed by year 2024. And you have already reached that 34 gigawatt. So big scope here. The communication and information technology. Our life really depends on that. Sensing and imaging, the lighting, the display, the healthcare. This is the big area, right? You saw the previous talk also. And this is the growth area. Today in US, you go to any university today, the professors today, this is the area they want to work on. The students here, all they want to do biomedical engineering, biophysics, bioscience, because this is one area where you can't export the jobs. They think that the jobs would remain here. So this is one area, the defense and security. If you are looking for money really for funding, so you have to work for the defense and security because they have the big pockets, they have big money. The LiDAR is a big opportunity. Now this is vertical cavity surface sampling lasers. Your new iPhone or new cameras with 3D camera will have an array of 32 by 32 pixels, about 1,000 devices, and pixels are used in optical interconnect. There was a question in the previous talk: could we make optical computer? Well, in the computer, the supercomputer, the optics is used for interconnect, and all the data centers you have to have optical interconnect. Otherwise, you'll be generating too much heat. So VCSELs is an important technology, material processing and low-cost manufacturing. This is one area where company like HMT should come in. I was in Surat in December, and I found that a diamond factory, they were using the laser for cutting the diamond. The place called Bodinakanur, I saw that they were using the cameras and artificial intelligence to separate the cardamom of different color, different sizes. The entertainment, that it is playing a big role. And this is the third. I mean, if I had to put my money together, today to start a company or to do something, so I would work on item number 13, food preservation and sanitization by UV light. UV light has so many applications. I have a slide later on, we'll talk about it. So this is one area, if you want to work in materials and devices, that should focus on. And the agri-photonics, smart farming. More food, less cost. Today in India, 60% of the population in agriculture sector, and they contribute only 15% of the Indian GDP. So there is a big scope here. So now this week we had this Clio conference. In the Clio conference, the field has grown up so big that it lasted for 5 days, and there were 18 parallel sessions some days. And the number of areas which were discussed here are listed. They're not. This is not a complete list, but a list where could be of your interest: silicon photonics, integrated photonics for neural networks, quantum photonics for computing, metrology, cryptography, communication, nanophotonics, nonlinear optics, UV, near, mid-infrared sources and detectors. The item number 7 is very relevant to India, right? Defense needs it. Microwave photonics, again, the defense application. Terahertz photonics, flexible display. Now, this item number 3, this is a disruptive technology. So there was a tutorial there at Clio, which I attended. You can attend it. All the presentation at Clio, they are recorded. And here, the flexible display, it's the game changer. I'll discuss it later. Optics and photonics for precision agriculture, artificial intelligence, free space optical communication, imaging, sensing, and application of technology. So these are some of the areas, right, which were discussed at Clio. And the interesting that 90% of the paper from universities, they are not from industries, because industries do not have money to do fundamental research anymore. Now, the biggest challenge for India and the rest of the world is China. In China, in the month of September, they hold this big expo in Shenzhen, which I attended a few times. And it's like a city, they have different halls there, and they display anything you can think about on Earth there. And these are the different technologies. You can think about where do you belong, where do you want to contribute. I would like to draw your attention to this Photonic Innovation Pavilion. This is more important to the research community, right? So you see the biophotonics listed at the very beginning, medical imaging, right? So you will find healthcare photonics again and again. That's where the biggest scope is. So if you really want to, here in US, you can go to any university. This is the hot area. All the students they want to do, they will not go for the regular engineering subject, they would go something relating to the biomedical engineering, healthcare. So these are the different areas listed here, which you may find that that a lot of innovations are taking place. Now I talked about photosynthesis. It's so important, and you can create here a billion-dollar industry. I mean, if you coming from a village or you have anybody there, you could advise them. They could have a small nursery in their home outside and send these. You can buy the planters and plant it and sell them. And you see the water and the carbon dioxide. When they react in presence of the light, then you have the oxygen out, right? So this photosynthesis is so important. Our body needs 7 to 8 liters of air per minute. 7 to 8 liters per minute. 11,000 per liter per day of air, per person. And so you need to have, your air. So yourself right now, because this COVID-19, you are at home, plant some trees or shrubs or something, at your home, purify. The students in your room, you should have 1 or 2 plants, and this requires something that some plants are good, requires less maintenance, and they do more purification. So encourage, your maidservant, your farmers, that they could have a small nursery and you can sell, make money, right? If you don't have space, you can have on your roof or anywhere, you plant this thing and you can have these plants in your home. Remember that we all are crew on this planet. We are not passenger. It's our responsibility, right? So there's a potential here, So I myself have planted about 350 trees and shrubs around my house. So this is the backyard of my house, where I planted trees. This is a panoramic view. You can hang on the wall, on the ceiling also, if you don't have space, you see. So there are ways that you can have multiple plants there. You can buy something like the planter like this, put in front of the window and plant it. This is the front of my house. You see, I have my solar system also. And all these trees were planted by me, and I generate like 5 kilowatt is the power plant I have, and I generate all my electricity, whatever I need. So while you are at home, think about it, photosynthesis, the solar system, solar lantern. So now, my field is the communication, the broadband communication. That's what I have been working on for last 20 years. Prior to that, I used to work on devices, lasers, detectors, HBTs, HAM, and I changed my field in 1997 to the optical networking. So it has taken about 20 years, the fiber to the home. So today, if you go do any management course, so they will talk about this is the Maslow needs of hierarchy. And here you see that you have the basic needs, food, shelter, clothes, etc., and then safety and security, and then love and belongingness. So self-esteem. So here, artha, kama, dharma, moksha, right? In that, you can translate in that fashion, right? Mahatma Gandhi, he just went for self-realization. He forgot about other needs. But today, our basic need is the broadband connectivity, the internet connectivity. Without this, we cannot live. When I was in IIT Guwahati, Gaganji took me to this new guest house. But then as soon as I reached there, it's a wonderful guest house. But he told me there is no internet here. I said, I don't want to be here. So went to the old guest house. So today it has become a necessity, right? Without this, we can't live. If your city, your town has broadband connectivity, fiber, the property value will go up. It is just like the highway, that you are connected with a highway. So this has become the basic necessity. Now, I told you in the beginning that we are at the beginning of the 4th industrial revolution, and this is what's going on. And you have to think, where do you fit in? So in this, there is no one technology. It's a fusion of technologies for making the system smart. And the good thing is that photonics is the core technology. No matter where you go, so you have 4G, 5G. Now 4G, 5G, you may say, oh, this is a wireless, what has to do with photonics? Well, 4G, 5G is only from the cell tower to your home. But how do you connect the cell tower to the core network? That is fiber, that is optical fiber. That requires optics. Then you have the broadband wired access network, right? Fiber to the home, anything, whether you get DSL or you have cable modem, all optical fiber. Big data, deep learning, machine learning, cloud, data center, fast processors, sensors, MIMO, optical interconnects, so it's all optics involved there. And that leads to artificial intelligence, robotics, drones, virtual reality, artificial reality, autonomous vehicles, wearables, IoT. And that leads to smart cities, smart villages, smart street intersections, enterprises, smart living. So the bottom line is that photonics is a enabling core technology, right? So the possibilities and opportunities are limitless here. So if suppose I had to start all over again, right? And what I had to do here in this country, people would ask, hey, what is the next big thing? What should I be working on? So this is it. When the smartphone came, that was the next big thing. But this next big thing is the applied, artificial intelligence, right? And now universities in US, they are offering a master course. And again, this requires different expertise. So in this course, they teach everything, because you have artificial intelligence needed in every part of the life, right? So they would talk about autonomous robotics, image processing, embedded systems, smart IoT, smart health. So everywhere. Now, this is one great application. This is for you guys, young people, could you design a divine robot? I feel that is a cool application of AI. In India, people go to temple, different places. Could you have a divine robot, like people go to a church, do the confession? That to this robot, you do the confession. You can invoke the presence of any lord or any god or any goddesses, and you can talk and you can get advice. So something like just think about whether you could do that. If it happens, then I think it would have a big market. So I just give you background because our life now depends on the network, and this is what I have been working on for last 25 years. But how does the system work? Just to give you a high-level background. So the continents, they are connected with optical fiber on the seabed, and that is called submarine cable system, right? You see all the continents connected with cables, and they have the names, right? So like you have the highways have the name. So every network has a name, and then the cities are connected by called long haul networks, core networks. One city connected to another. In a particular city, you have a ring. It's called metro ring. So when traffic goes in both directions, so if there is a cut for any reason, so your network is not broken, the signal can go in the other direction. And you can have from the ring connect your enterprises. If you are enterprises like big companies, right? Your railways, your defense, so that is called enterprise network. Or access. You have single fiber coming here, and you have a splitter optical fiber, and then you connect different residences or offices. So this is access network. So in Huawei, I have been working on the access networks. And in the access network also, there is a convergence. No matter what you have, whether you have the fiber to the home or copper DSL or coax line or Wi-Fi or wireless, there is something called convergence. So this is how it works. So I had this particular system in my lab. So this is called OLT, optical line termination. So you see in the middle, the two cards here. So these 4 ports here, they are connected to the network, core network, right? I mentioned that the core network. So this guy sits somewhere here, and these are the different ports, and each port, like here, is connected to port here. Now there are different systems, like you have 2G, 3G, 4G, 5G in wireless, in optical fiber also, fiber to the home also. There are different generations. This is GPON, XGPON, TWDM PON. So in India, actually in most of the countries, they are deploying GPON, means 2.5 gigabit downstream and 1.25 gigabit upstream. And this is a shared network. So you have a single fiber coming here, you put the splitter, depending, it comes here in the neighborhood, and you can have a splitter 1x32, 64, 128, and they are connected to the home or offices. And the fiber is not there, You can also bring the broadband to your copper line, and that is called DSL. Here is the DSLAM, digital subscriber line access multiplexer. Here you multiplex the traffic from different homes and you bring copper, or you can have the cable modem. In India, it's not very popular, but in US, we use cable modem. At my home, I'm using cable modem. You can have public Wi-Fi. Over here, you see, you have cell tower. So it's a wireless, that's where you are getting the traffic, but this guy needs to be connected to the network. So here one fiber can come here. The bad part is that this fiber to the home, India, I think there are two companies. I'm not sure if there is any other company, but the Bharat Fiber by BSNL and Jio Fiber, they are installing the system. And I got this number in India, there is only 1.3 million lines today. And just think about in China, there are 350 lines, 350 million lines. Unfortunately, despite the cheap labor in India, the cost, per line India is the highest. This is the number I got, reported number, $1,580 as compared to $200 in China, $500 in US. I know that India has plans to connect every village. And now, because of the COVID stuff, now we realize the importance of the broadband. So this gives a great opportunity, for the whole country to go for broadband, right? To increase the bandwidth, connect every home, connect every businesses, because it's so important, right? So India has 99 cities, smart cities. And these are the first 20 cities, you already know it, I don't have to tell you anything, but a smart city, again, the backbone of that is the broadband network. If you don't have broadband network, you don't have the smart city. You will be putting, a lot of surveillance, vigilant cameras. You will be connecting all the offices for increased productivity, increased GDP, new jobs, environmental impact, consumer benefits. So you see the number of applications here in the smart cities, and this offers a huge potential. The universities, I feel that if you really want to get into this, because there's money here, right? The cities have the money. Central government has allocated the money and they don't know what to do with that. And this requires background in different areas. So if in the university you set up a test bed, these things are not expensive, by the way. These cameras have become cheap, the router and switches, they are very cheap. So if you develop a test bed, you may find that chief ministers, the prime minister will be visiting your lab, and the money would come to you instead of you going and asking money. Now, as you heard in the previous talk, whatever you do, you have to think about some practical applications. So if you are building something, right, you have to see whether you can make something out of that. And normally you would make a prototype. If you are working in sensor, you have to get the data out of the sensor. And for that, you have to use different kind of, I/O, right? Input, output, the protocols. And the wireless protocol, most famous protocols are Bluetooth, Zigbee, Z-Wave, Wi-Fi, LTE-U. LTE-U is different than LTE, what you must be hearing. This is unlicensed. Unlicensed means you don't need a license. You can have it in your, like in IIT-Guwahati, you can have LTE-U. So LTE-U, you are not connected to the network. You are connected inside. So these different protocols, they have different speeds. The distance they cover is different. The data rate they support is different. The energy they require is different. And if you have different sensor, different places, right, you would like to use a protocol which uses very little energy, right? So the battery lasts for 6 months or 1 year or 2 years. So for that, the Zigbee and Z-Wave, right? So if you have temperature sensor, if you have want to measure the humidity, all that, so you would be using these protocols. So to my youth in India, if you are in the university, if you are a research scholar, use your time productively. Acquire expertise in data acquisition. This is very important. If you can create the wealth or you can build something, but you cannot get anything out, it's useless, right? So if you are creating knowledge, if you are building a sensor or doing something, you have to get the data out. So the data acquisition, and this is very simple, by the way. There are boards available there. You can buy for very inexpensively, you can make in your own lab. So data acquisition board and the A to D converter, D to A converter, the DSP, the wireless transmission, amplifiers, power supplies. So these things you must get, some basic ideas, because this would help you in building the prototype. And they are not very hard. Today, you can go to YouTube, right? And you can learn anything about. There is just so much free resources available, free books are available. And these things are inexpensive also. For low speed, you can just buy it, And in your lab, if you have this platform, right, then you can just quickly go and put them together. So right now, for example, if you want to buy a test and measuring equipment, they have a common platform. They use the same keyboard, they use the same display, power supply, and actually they can, through software license, they can convert one instrument to another. Whether it's oscilloscope, want to convert oscilloscope to a spectrum analyzer, just by the software, the license, you can convert it. So the platform is common. And that's the beauty of the digital processing. Now, this was a talk at Clio, the flexible display. And this is a game changer, because this flexible display, like the folding your phone, or because it will take the shape of whatever you have. If you have a shirt, there will be a display here, so it doesn't require, so it can be folded. So it has multiple applications for the smart home, for the office education, your entertainment, right? So it provides a flexible platform, fully flexible display, fully flexible sensor. So this, I would recommend that each of you attend this talk, right? This is the company in China. And if you're looking for a job, try if they have openings here. They love Indians, by the way. In China, they love Indians. The Indians are very good people. They know that they are great contributors. They know English. They can interface the world. So they have great respect for Indians. So you look for, if you are looking, because this is the disruptive technology. It will change the whole thing. So see if you can find jobs over there. And the technology is very sophisticated, the multiple layer here for the flexible display. Now, if you are looking for like joining defense services, right? As I said, the defense have the money. They can give you money just like that. The universities which have partnership with the defense, they can really get a lot of money. So this shows like an aircraft, like a jet fighter, right? What kind of network you will have. And they require optics. The top here, this is a cargo plane. I used to work in this area. I had a contact from Air Force. In a cargo plane C-70, you see this spaghetti, right? All the cables were very thick cable, carrying the data. In a typical jet fighter, this is the communication network. You had different radios, right? High frequency, VHF, UHF, L-band, joint tactical radio system. You have satellite communication. You have common data link converts to the Navy system, to the Army system. So the communication network and optics is the backbone there, right? Then you have vehicle management system, right? You have to do all kind of recording, vehicle monitoring, system management. Is again optics here. The electronic warfare. Now, electronic warfare is the big thing. I don't know if you know electronic warfare. It means that you have the right on the electromagnetic wave spectrum, and the enemy does not. Because if enemy does not, then they cannot communicate, and you will have the right. So today, this is the big area, electronic attack, because in the audience, you may have some RF engineer here. So this is a big area in US. All the defense companies, they work in there, right? Electronic attack, electronic protection, electronic support. And again, this is connected with to the optics. You have the navigation for that, again, optics. And here you have the storage. All the data need to be different file server. And again, the optical fiber. Now here are different sensors. You have the radar, you have the thermal vision. So this is the different data acquisition systems, right? For the identification, surveillance network. Again, they are connected with optics. So if you want to get a job, you want to work with for NAL, for HAL, for Air Force, I just want to tell you that the optics is there too. Now this is on Clio, right? This is JPL. A friend of mine, he gave a talk, and I think it's very relevant to India. SSPL in Delhi has been working for a number of years. These are the long wavelength detectors, right? They are used for imaging, right? In the dark. Our soldiers need to see what is on the ground, right? At night time. Our plane need to see what is there. And here, the different kind of material. Traditionally, they used 2,6 mercury telluride. That's what SSPL has been. I knew that because I visited them a long time ago. They use LPA to make these detectors. But it's very difficult. 2,6 compounds, so there are new materials they're working on, the quips. And now he gave a presentation of using indium gallium arsenide and antimonide and different wavelengths starting from 1 micron to 12 micron, covering near infrared, short wave infrared, medium wave infrared. So whole spectrum. So this is one area for the research in the universities in India. The LiDAR, this is for autonomous vehicle, for the agriculture, for the river survey, modeling and pollution, archaeology, building construction. This is again a big area for the universities in area. A lot of applications, depends on your imagination. Now, agrophotonics is the word, 5 trillion that contributes to the world GDP, which is like 80 trillion, right? And here, the optics here, it could be several $1 billion, right? And here the different applications of photonics. Here you can predict the protein level, determine optimum harvesting time, map water quality, screen crop for contaminants, monitor overall soil health. You can have a small drone and can go over the field and figure it out, what the health of the crop. In India, as I mentioned earlier, 60% of the population, they depends on the agriculture. And they add only 15% to GDP, and they are in very bad shape, right? They don't have access to the free market. They need to increase their productivity. They need to reduce their cost. Otherwise, farmers are suiciding. So this is something that the scientific community need to address. Now, this is one area of for the farming. Now, because the land is disappearing, agricultural land is disappearing, and you can do farming at your home, in your basement, in your attic, using LEDs. So this is another area, right? This is the people in Japan. They are exploring this, Japan and South Korea, right? The blue and red LEDs, they have been found to be extremely effective source of light for indoor farming and are becoming increasingly popular in Asia, right? Red LED promote the root growth, while the blue LEDs promote chlorophyll production and leaf growth. So one area, but the most important thing is that this is another big research area, and I guess Calcutta University does have a project on this, the UV LEDs. And UV LEDs, this is from the US Department of Agriculture, right? They have the strawberry after 8 days. You get spoiled here, but they were, exposed to UV light and they remain as fresh. And you see here with UV based, UV LEDs, what are the different applications in the communication? By the way, this is the great application for the soldiers on the field is called non-line of sight. Because the scattering of the light, right, is inversely proportional to the wavelength to the power 4. So the UV photons, they get scattered. And so you don't have to have a line of sight. So you can have a phone in your hand, just like you have the phone and use the RF. So the UV for the short duration is no line of sight and quite useful, right? So the water purification, your appliances, the washer, fridge, you can just use, the applications are, depends on imagination in medical and security and plant lighting. And right now they use mercury lamp. It's huge, it consumes a lot of power, right? And it becomes very hot. And if you can replace it with a LED, right, it becomes so small. And if you go to Amazon and look for the UV sanitizer, they already have a product. They are selling it like for $130. This guy, so this is already a product, and you can think about this in India, it could have a huge market. For medical, for every part of the body, right, there is a diagnostic device based on photonics. I don't have time to go into details, but SBI actually has a poster, and it shows that India, when I go to India, their setup, with the testing company, you know, they get a cut out of that. So it costs a lot of money. So a lot of things you can do yourself, right? So if you go for you know, like here massager, right? 980 nanometer laser can penetrate and can do the wonderful massage. So the LED is just to focus it. So you have so many devices at your home, you could use them for application. Now, this is a success story in India, right? You have the solar system here in India. I'm so impressed that they are installing a solar system on the lake. Actually, my state UP just announced that they would be building a solar plant on the Rihan Dam. 150. There are 41 solar trees. They produce, you know, 182 kilowatt power. So, the Dell building somewhere near Bangalore, they have this vertical wall on the wall, solar panels here on the river. So, scope is huge in your villages, in your pond, in your river, and you can create a lot of opportunities here, right? If you have the poles in your town, put the solar stuff there. Now, this all I've done. Now, this is some few slides I have to show you what is happening in industry. There is a changing of the industrial culture today. In 70s, efforts were on research, big effort on research, and then on development. In 80s, equally, research and development, people started thinking about, hey, whatever you do, it has to go and developing a product. In 90s, less money for research and more for the development. So the companies, I'm talking about US, they were spending like 1% of their revenues on basic research, 9% on product development. So when I joined Bell Laboratories in 1985, the core Bell Labs, we had like 300 people, 800 people there. And AT&T had at the time $33 billion budget. So they were giving 10% of that, like 3.3 billion for R&D. And of that, 1%, it used to come for basic research. There I was. So they have budget. Our vice president, Arno Pengia, has like $330 million budget. And we were like 800, 900 people. So each of us has a budget of $300,000. But now it has disappeared. The companies, their revenues are going down. The base old model has disappeared. So only the universities are doing now basic research in government labs. So if you see the program, you may find that all the papers, actually more than 90% paper, they are coming from government labs or universities. If they are coming from industry, mostly from China or one or two industry in West. But in 2000s, this century, in the West, the efforts is on integration and services. They feel that if you can buy the milk, why do you want to own a cow? You know, they got rid of the basic research, they got rid of their component manufacturing. They felt they can buy from China, so they put them together. So the companies have become fabulous. They get the packaging also done outside. All they do, the design and development. So there are foundries for the materials and crystal growth and assembly and packaging. So the design, development, marketing centers, like if you go to Cisco, they don't make any devices, but they have the ASIC application specific ICs, and they use the foundries. So most system companies in the West are now design, development, and integration centers, right? So what is important is system of systems, fusion of technologies, and the outsourcing. And this is a great benefit for India, right? Because in India, you could now, this COVID-19, right? I'm talking to you, right? All of you sitting here. So you can also now get employment in any Western company and work from India, right? But if you want to enjoy the research, then stay with academia. In industry, they would like to see, hey, who's your customer? Why are you doing this? So, and if you're in academia, do good physics and further the scientific knowledge. Develop prototype to test your concepts and transform science to technology. If you don't do this, the chances are that you will be struggling for funding, right? If you have some concept, if you have a lab, you demonstrate something, you invite the politicians, you invite the government officials who have the money, then they would be impressed and they give you money, right? So always, whatever you do, have an end application and customer in mind, right? That is a big plus. So if your students are working on terahertz or something, they should know why are they working on it, what the end applications, right? So question comes, what is the big challenge and opportunity? The big challenge today is cost. low cost, low cost, low cost, low cost every time. And China is the winner. They try to get the cost out of it. So whatever is the cost today, they will be pushing their supply chain. Hey, you have to reduce the price, right? And everybody wants more functionality at reduced size, weight, power. So these are the buzzword today. If you want to go, you can get funding from defense, from anybody. If you can reduce, this is called swap, size, weight, power, and cost. If you can reduce it, say light bulb. Light bulb has been there like for 100 years, more than that, right? But if you can come out with a new light bulb which consumes less power, then you are a winner. You can file patent. Even today, people are filing patent. People are doing PhDs, right? Because of this. Can reduce the cost, can reduce the size. So you have LED lamp. That is the product of, because people want to reduce the power and cost, right? Now, other most important is quality of experience. And this requires continued innovations with friendly human interfaces. You love your smartphone. Why? Quality of experience. Anybody can use it. It doesn't require any scientific knowledge. You don't have to be an engineer. And you have a powerful computer. You have your smartphone. I don't know if you realize that. Ask how many radios it has. It has at least 4 radios, right? It talks to the satellite, GPS. It has Bluetooth. It has Wi-Fi. It has the 3G, 4G. So it is multiple radios, it is a computer, it is a watch, it is a calculator, it has everything there, right, through the app, right? So this is called quality of experience. So even if something is available in the market, you can come out with a new product, provided with better score, QoE, quality of experience. That would be a winner, right? So nowadays, you can have the design, development, manufacturing, and marketing across the globe. You don't have to have a vertical integration. You don't have to do everything yourself. You can buy the modules, some modules, stuff, put them together, because the product development cycle has reduced. The lifetime of an engineer has reduced significantly, right? There is a lot of global competition. So these offer bigger opportunities and challenges to us, right? Now the cost of, these are opportunities as well as you have to understand a lot of people, they talk garbage, right? So they talk about that we will do integrated photonics, we will do this, we will do that. So these 2 slides I would have just to tell you the reality, right? So the barrier and limitation to reduce cost of photonics chips. The size of laser or detector, it does not reduce because you need a minimum volume. If you want to get a certain power out of a laser, then you need to have a certain number of photons. And when you have one pair of electron and hole, they combine, you get 1 photon. So you need to have a certain cavity volume, right? So you can't reduce it. And if you have this cavity, it could be very small, but for handling, you still have to have the chip size, like 250 by 250 macron by 250 macron, whether it's a detector or the laser. So you can't reduce the size. People think about the silicon. Oh, silicon is getting bigger, device getting smaller, but you cannot, scaling does not work in optical devices, right? Also remember that an optical device is a 4-particle device, right? In electronics could be a single particle, right? If you take a MOS device, either electron or hole, right? You take CMOS, they are both electron and hole, but very little power consumption. But in optics, you have electrons, you have holes, you have photons, you have phonons, which is crosstalk, right? So you cannot have too many devices together. You may find that one device would hit the other device. Hey, are you guys able to hear me? Hello?
Yes.
Okay. So you have the optical power coupling, how to get the power in, how to get the power out, right? And you need 3-5 semiconductors for optics devices. The wafers are fragile. You cannot have 12-inch wafer like in silicon. Mostly 2-inch indium phosphide. When I started working on liquid phase epitaxy in 1918 in Sheffield, England, my wafer size was 1 centimeter by 1 centimeter, and that itself was very big. Now you can have indium phosphide 4-inch wafer, gallium arsenide 6-inch wafer, and when you have 3-5 compounds, right, you have to also think about that. You have to have stoichiometric defects. You need to have exactly 50% group 3 atoms, 50% group 5 atoms, and if that is not the case, you have stoichiometric defects. These 3-5 substrate, they also have low thermal conductivity, so the device gets heat up, and if temperature goes up, the performance goes down. If you want to make a PN junction, which is necessary for any source or detector, then you require p-type impurities. And p-type impurities are normally zinc. It diffuses very fast. very difficult to control. So the integration is not cost effective, even if it's technically feasible, because yield is reduced. If you think about that, if you have reduced 10 devices you integrate in photonics, right? If you have yield 90% for each device, so you combine, multiply 0.9, 0.9, 0.9, the end result would be significantly lower. Now, many times people would say, and you can fool people, you can get a lot of money. Oh, we would like to have one chip solution, we would like to integrate lasers and detectors, but you can't do that. They are totally different devices. One requires forward bias, the other one requires reverse bias. One requires very high doping because you want to have more electrons and holes, and the detector requires very little doping, no doping. You would like to, have electrons hole generated there by photons. So different devices, right? You have crosstalk, electrical, optical, thermal, and signal launch. So the processing technologies, electronics and photonics, people will talk about, oh, we can integrate both of them. No, you cannot, because electronics and photonics, they involve different growth and processing technologies, right? So this is the most important slide I have for people who may be working in integrated photonics. You need to understand the limitations of the technology, right? So communication lasers, communication I'm talking about, a detector can't be made in silicon. Of course, you cannot make any laser on silicon because it's an indirect band gap material. And you can make lousy silicon germanium detector on silicon, but there is a 4% lattice mismatch. So there are defects there. The device may work fine in the beginning, but as temperature increases or with age, the defects become electrically active and the device will die. Silicon is very good for making passive components, the modulator and the waveguide, right? Because they require large real estate. Remember that here, this is the important thing. Electron is very skinny. The de Broglie wavelength of 1 electron volt electron is just 1.3 nanometer, and that's why you have electron microscope, right? You can see very fine dimension, very high resolution. With 7 nanometer CMOS technology, you can have more than 100 transistors in 1 micron square area of chip. You can integrate 1 billion of transistors in just 1 millimeter square size of silicon chip. Whereas to make a laser or detector, you need 0.5 millimeter by 0.5 millimeter, 0.25 millimeter by 0.25 millimeter, right? So the electron is skinny, but photon is very fat. 1 electron volt photon is 100,000 times, bigger. Its wavelength is 100,000 bigger, 1.24 micron. So a typical passive photonic component can't be made smaller than the wavelength of light. So this is the problem of physics. So no Moore law or advanced photolithography can overcome this. So you need to have waveguide. In the case of electronics, silicon electronics, you can have a very nano wire, but in photonics, you need to have waveguide that requires area. It's very expensive to replace transistors with lower functioning photonics modulator. Like somebody asked in the previous talk, can you make a photonics computer? The answer is no, because of these reasons. You can use photonics for interconnecting the different boards, interconnecting the high speed, this thing bus, you can use that. So beside a hit on yield, relatively small area, 10 micron by 10 micron, lousy modulator can require a replacement of 10,000 transistors, a huge price. So the no chip manufacturer would like to, sacrifice this. So due to physics and economics, it makes no sense to merge photonics and electronics, monolithic integration on silicon. Photonics on one wafer, electronics on another wafer, and then house both of together is more realistic. So this is the message I want to tell you, because today we start jumping, talking, we can do that, but that's all wishful thinking, okay? Now, this is the biggest challenge, how to reduce the cost. Major cost today is in packaging, and I told you that the electronics and photonics go together. So these are the laser chips, and these are you have the transfer impedance amplifier, laser driver, or these devices, they need to be packaged, here carrier on chips, and then they need to go in the housing, and then they get the final devices. The goal is that reduce the footprint, reduce the size, So now you see that here, this is the BOSA. BOSA means bidirectional optical subassembly. It has both a laser transmitter and a receiver. Right here is a TOSA, BOSA, here 4 channel. So this guy can handle 100 gigabit per second, right? This is active optical cable. It has a transmitter receiver at both ends. It can replace your electrical cable, right? You won't know interface here is electrical. So the idea is reduce footprint, simplify electronics, reduce number of components, optimize power dissipation, avoid crosstalk, simplify packaging, and it has to be scalable, repeatable, power efficiency has to be high, and volume production. If you cannot have volume production, your cost will be higher, your technology will not go anywhere, okay? Now, this slide shows the challenges specific to India and their mitigation. So while talking to people, I actually used to work government of India. I was in charge for the industrial licensing to the electronic component industry. So I visited most of the component industry all over the country. Later on a United Nations doctoral program, I worked national labs also. I talked to a lot of students and faculty members. So this is my conclusion. It might be totally wrong. You have to draw your own conclusion because I'm away from India for last 40 years. So what's the problem in India? The lack of technology awareness. The funding authority do not know what is up-to-date information, especially the photonics people do not know. They only know the optics. So the funding is an issue. Infrastructure and culture for product development is missing, right? Because there is no end use, industry is not there, industry-university collaboration is not there. So experimental facilities and maintenance in universities. Even if you have the facility in the universities, who will maintain it? Because it requires a full-time technician, full-time this thing. If you have crystal growth, it requires liquid nitrogen, it requires power 24/7. So these are the problem, the ownership. Because ownership is a problem. If you go to any national lab and you dig a hole, you may find that some different kind of directors coming there, assistant director, deputy director, additional director, director, senior director, editor director. And once you are at director level, you don't have to go to the lab. So this is the situation that the ownership is not there. You know, on one thing, 10 people working, then nothing happens. If one person is responsible, then things start moving. So here in West, the ownership is there. One person, if you have like a crystal growth or anything, the person has the ownership, he decides and he has to deliver, otherwise he loses his job, right? The collaboration networking is kind of, I feel that is missing in India. The industry-university partnership. So like even your department, if you are there, have a industrial advisory board, invite industry people, tell them what you are doing, ask their advice. Just getting them on the board, you know, you will get a lot of benefit. They will hire a student, they will provide you some funding, you know, and the trust in business. A businessman is considered a thief, you know, he'll run away with money, he'll do this, that thing. And I found that in India, urgency is not there because people think that, oh, there is another life. If you can't do in this life, we can do in the next life, or what's the hurry? Don't take stress, don't worry about it. Sab chalta hai. So these are the kind of things I noticed, right? There is a misuse of funding also. Some people get a lot of money, and when they get a lot of money, it's just like flood, you know, and then you can't use that water, right? It goes in the ocean. So people, they end up buying some useless stuff or the wrong stuff. They do not know, no maintenance, it gather the dust, and they don't want to share with others, right? So more interest in journey than the destination and results. Too much politics, mostly theoretical, and many times irrelevant teaching and research, not many industries. So these are the stuff. This is not my stuff. This is what I gathered feedback. Now here is I feel, this is my feel that what could be you. First, realize your true self. You know, you are the best, you know. And you be the change you want to see. This is what Mahatma Gandhi said. You know, don't believe that Bhagat Singh should be born in my neighbor's house. You decide what you want to be. You have to be assertive. You, the students, you have the power. Your professors do not have the power. If the director of the institute tells your professor, don't do this, then he will not dare to go against his or her instructions. But you are the students. You are not covered by anything. So you be the assertive. You decide what needs to be done. And you have the power, you have the voice, and the politicians, everything, right? When Prime Minister goes different places, he said that India's strength today is the manpower under 35. So make use of your power, right? Take ownership. Explore local, national, international collaborations. Don't be afraid reaching out people, but prepare to listen no, right? Find partners where you could do experimental work. It's very important. You may not have a lab, you may not have anything, right? But somebody else has it. And don't worry about that you will have, they will steal your technology, they will do this. Let them steal it, The thing is that they can write a paper, you can write a paper, but you would be the winner at the end, right? So find partners. So you're looking for a laser, then see who has this device in India. And how to find that, right? You can ask the manufacturers, hey, is there anybody in India has it? He will tell you 10 places that go and they have it. So all the sales people, marketing people have good relationship. Take them for lunch when they come to you, and they can share a lot of information. Always visit expos wherever it is. Never miss any. Meet and talk to the industry. See what is the new product, and they may have jobs. They may like to collaborate, and try to work more than one project at a time. Some near term, some long term, right? So near term brings you money, cash flow, right? And long term, you can do this thing, right? You have to earn your right to do on long term projects by delivering it. So if you deliver something, oh, you are a great, okay, no problem. You have this much money. So you have to work, you have a balance, right? Long term, short term. You cannot just think about doing long term and no delivery, right? And be your own boss. Compete with yourself. Have a balance, work on both near-term, long-term projects, think outside the box, and have industry involvement. I'm involved, I am the Stevens Institute of Technology, I'm their own industrial board, do nothing, but they invite me, they invite many other people there, and we meet together, and they feel good. So in your board, in your department, have 5-6 people now, because now we have the virtual meeting. They don't even have to visit you. Just have a meeting, tell them that these are the courses we are teaching. Is there anything we can do here? And get their advice. And you make friends. When you want to make friends with somebody, don't seek help, seek advice. And these people will become your friend. Now, I'm sorry, I have 2-3 more slides, and I'm taking out of my time. But so now what is happening? This is to the benefit of India, like hardware, software, firmware, blueware. The hardware, it continues to get smaller, better, lighter, and cheaper. And this is a challenge for India. That's why a lot of companies are going bankrupt. They can't survive. They can't compete with China. But software is getting bigger, more complex, and expensive. And that's the big advantage and global opportunity for India. Remember that in a system, as the product matures, 50% cost is hardware, 85% cost is software. And many projects fail because of the software, right? If your cell phone today, smartphone, right, the major cost is the software. So what is moving towards software-defined reconfiguration system? So what I heard was that like Geo, right? They deployed the system. Why? I told that they got the white boxes from South Korea. I don't know if it's true or not, but somebody told me that that's what they did. They hired the engineer. They wrote their own software, right? So the cost goes down. So, so consider having a solid background of both hardware, software, both theoretical and experimental. Think big picture, end user and application. Build prototypes. And this is most important. Attend courses on system engineering and project management. Because if you are in the university, you are a student, and university might be offering these courses. But if you take a university job, you will be managing a project, you may be managing a program, and this would be very handy. And system engineering is putting the resources together to make something happen. The thing is that if you want to start your own company, which with the Prime Minister is emphasizing, they have fund allocated, then some of my thoughts here, right? Digital India today has millions of programs and problems, and so are the opportunities, right? Technology can address them. Invite business, industry, defense, and city leaders to your department, to learn about their needs and wants. Look for what society needs, and then try to invent it. Visit expos, find better way of doing the existing things. Do brainstorm within your department, and come out with ideas, select a leader on a rotation basis, record minutes, prepare a quad chart, and one chart only what you want to do, what the problem you are trying to solve, right? And the golden rule is that decide what you want to do, and then find out who has the value for it, and then make them pay. Develop concept prototype as part of your classroom projects, and the technology, your own R&D, collaboration, CSIR, where to get that technology from. The CSR laboratories, they have the facilities, technology, and nobody is using them. Go and talk to them, right? Have collaboration, provide clarity when none exists, and create energy. need to work under resource constraint space. You can provide products and services to anyone in the world. Think about these companies, Amazon. They don't have any manufacturing business, but they sell everything under the sun, right? Uber, they don't own any taxi, but they provide the taxi service. Facebook, they don't own any content. People create the content and using that, like Netflix. They don't own any theater, but they offer the the videos you can watch anywhere. Alibaba, they don't own any manufacturing, but they can put you in contact with the millions of companies. Bed and breakfast. So think about that, because you could oftentimes you feel that, oh, don't have money, don't have this, but on those lines, So the important part that you had to have a built-in driving force. If you crack inside, right, a beautiful bird will come out, right? But if you crack from outside, somebody has to crack you, right? Then you are just the food of somebody, right? So just remember that it has to come inside you. But right now, if you are at the beginning of your career, or you are in the initial phase of your career, you have to select things which you enjoy. Select the career carefully and change it necessary, right? I changed my career. I used to work Government of India. I was a class 1 graduate officer, and I felt that it was not my cup of tea. I was just wasting my time. I had the passion for technology. My wife was professor in Ghaziabad, and I applied for a Commonwealth scholarship. I got it, and I left India. And I have the possibility going to teaching, but I had the passion for industry, product development. So I ended up in the industry. So I could work for the government, right, where I was doing more clinical job, technocrat, and go to the world best place in Bell Lab. So you can do whatever mind can conceive, mind can achieve, right? So enjoy what you do for living. If you do that, then you don't have to work, right? When work is a pleasure, life is a joy. Remember, this is the Karma Yoga. When some people tell you, oh, you have the right to your work and not the right to of fruits, that's bullshit. We are the authors of our actions. But remember, results are subject to the hidden law of nature. We do need the results. But if we don't get what we want, it's because there are a number of hidden things, right? And so the one thing this quote I found is true in most people's cases. I rarely end up where I was intending to go, but often ended up somewhere that I needed to be. I never thought I would work in Bell Labs. I never knew about BA systems. I never knew about Huawei, but I ended up there, and they were the right places. So watch people around you. People play multiple roles. Find which role appeals to you. Ask where do you want to be after 5 years. Consider your personal values and circumstances. If somebody says, hey, there's a lot of money, sell the alcohol, sell the cigarettes, BDs, I would like to go there because that does not conform to my personal values, right? So more you plan your career, better you can face unplanned events. The important thing in the life is find a mentor. And this is one thing that you will find that all successful people will tell you, my mentor told me this, my mentor did this, right? And ask if you do not know, So all our Upanishads, Bhagavad Gita, they are Q&A, right? In Bhagavad Gita, Arjuna is asking same thing again and again. And Krishna is replying, right? The entire Gita was finished in chapter 2, but he kept asking. So ask anything you do not know. Don't be afraid of, right? A mentor listens and gives advice and objective feedback with our interest at heart. Help us at the time of distress. Identify our internal strengths, weaknesses, opportunities, and threats. One in your organization, can teach you the corporate culture and valuable career moves. It's a two-way street. Your mentor helps you, and you do you help the mentor. It's called reverse mentoring. These days, I'm learning from my grandchildren. I learn a lot of things. I see what they are doing, and I actually ran an election for my board of education in my town and dealing with the high school, students, and I learned what they are doing, right? So every great achiever is inspired by a great mentor, and I do not know if you know that he is the commander-in-chief of Sri Ram's army, right? But he had a curse. His curse was that he did not know his strength. Somebody had to remind him. And that was for good reason, because if he knew his strength, then he could be Ravan, he could misuse his power. So there is always some switch somewhere, right? So people have to tell him, hey, you can do this, you can fly, you can do that, right? So that curse we all carry. We do not know our strength. So if you have a good mentor, he can help you, tell you, right? Or your friends, your colleagues. So recognize and realize your hidden strength and inspire others to find that, right? But the important thing that they go an extra mile. Most of us, we go 99% and leave the last one. Oh, we can do it later. Oh, it's okay. A little part is left. We can finish it. We can come back. No. Whatever you're working on it, finish it, complete it, go an extra mile, right? But always be part of the solution, never a problem. If you go to your manager or anyone and with a problem, nobody wants to hear problem. They will say he's a problem maker, he will be a problem, he will say, oh, I don't have time today, oh, I'm doing this, I have to go and meet my doctor, I have a dentist appointment, blah, 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 blah. But if you go to with a solution, then this person would be willing to talk to you. So always go, first find out what is the solution, go with the recommendation. And if you do not have the solution, then you go for advice. You don't want to go problem. Nobody wants to hear problem, right? And the important thing, go and get it. That's what people like it. So in India, I'm sorry to say this, but some communities, they are that belong to that category. Like if you see people from Punjab or people from Gujarat or people from Sindh or Marwadis, they can make things happen. They can go anywhere. They make jungle mein mangal, right? So keys for lifetime employability, right? Find mentor, behave like less like an employee, more like an owner, right? Dedicate yourself to creating, selling, delivering values. View your employer like a customer. Invest heavily in your core skill and technology. Develop soft skills. Refine your communication skill. Be self-managed, self-reliant. Work on winning projects. Develop teamwork. Teamwork is very important. If you cannot work in a team, people will not hire you. They will push you out. So it's extremely important. Okay. And be ready for disruption. What you are doing today, tomorrow it may not have any value because there is a digitization, Uberization, the Uber. So these things have become word now, right? So outsourcing, merger, acquisition, restructuring, downsize. But if you are true, you are honest in the respect, if you have this quality, they are priceless. And take a lesson from a tree, stand tall and proud, be content with your natural beauty, drink a lot of water, remember your roots. Be useful to the society by offering whatever you can, verify your surroundings, enjoy the view and your true nature. During this time when you are at home, plant some trees, shrubs to purify air and beautify your surroundings. So this is my summary. This 21st century that belonged to photons, like 20th century was to electrons. Artificial intelligence and broadband access network will change the world and lead to the fourth industrial revolution. Photonics offer unprecedented opportunities and challenges. Read tutorials, articles in IEEE journals, magazines, newsletter, technology trends, and keep yourself up to date. Pursue every opportunity to gain first-hand practical experience, attend conferences, trade shows, job fairs, and build network of friends and well-wishers. If you are in a wrong field, change it. Position yourself to build a successful, enjoyable career in digital India, smart and skill India. Don't hold to a familiar pain. Consider trading into unfamiliar pleasure. And that's all I have, Jeff, and good luck. So I'm sorry that I had taken more time than I was supposed to, but I wanted to share this. Any question, Gaganji? Anything, any comment?
Thank you very much, Dr. Chand, for this very informative talks and briefing up about the photonics, where does it stand in India and what are the potential, what are the prospects basically in India and where do we stand. So thank you very much for this such a wonderful talk. We have a lot of comments and lot of questions for you.
Sure.
Actually, there are some questions of general nature. Can we convert it to a general discussion?
I can't hear you properly. I can't hear properly.
You cannot hear me, or do you?
I can hear you, but the question.
Okay.
Mr.
Professor Basanta was speaking. So what he's saying is that since we had discussed about this session, maybe we can have it more interactive session. Maybe audience can ask questions directly from you, and probably you can answer. but maybe if you allow me, I can some of the questions that audience have for you, I can
Yeah.
speak them out here. Is it okay now, Professor Basanta?
What I am saying, there are some questions which are of general nature. So if I think some of the questions are of academic type and some are application type. So if some faculty members are still present, probably, so we can also probably answer. We can.
Okay, let me ask you some very general questions without going into the technicality. Okay. One of the question is that, in India we have a lot of money being pumped into the solar devices, but what is still hindering the large scale production, solar panel modules?
Yeah, so what is the question? What is that?
What is it that is hinders the large scale production of solar modules in India, solar panels? Why
Yeah, but
we
I
are-
still don't understand. What do you want to know about that solar panel, large scale production of solar cell? Solar panel?
why it is still not happening in India? That is the
Oh,
question.
why is it happening? Well, you had to answer that question. I don't live in India, right? So you should know the answer why it's not happening, because what is happening is that sometimes what happens that trading is more profitable. So if somebody has to produce it, may find that the cost of production is more than the price they had to pay in China. But this the question which you people have to answer. In old days, what was happening is that the industry was protected. There was a tariff through customs duty. There was a import restriction, and that you cannot import whatever is made in India. But to give you a little background, in 1977, when the Janata government came after replacing Indira Gandhi, they changed the policy. Earlier, there was a list, import and export trade control. In the import, there was a list of items which you can import. Rest you were not required to, you cannot import. You need a license. But when Janata government came, Mohan Dharia, he was the commerce minister, and he changed the policy. He said that you can import anything except what is not listed in the book. So, and with the result that the import is allowed, you can import anything, right? And because of that, I guess there is no large scale production. Plus, you need to push you to, in China, because I work for the Chinese company and I travel a lot in China, the Chinese government is supporting their industry. Because it is a communist country, right? The government decides, hey, you will be buying so much from so and so, so much so and so, so much so and so. So if the government of India tells, like in India, you have Solar Corporation of India, right? If you tell them, hey, you have to buy so much from the local company, so much for the local company, then this company can grow, right? But that protection is not there. And I guess that might be the reason that you don't have the large scale production. And this is what I tell, but this is the frustration of many people in our this WhatsApp group, right? When this Professor Singh, Rajendra Singh, he went to India. He said he spent $250,000. He wanted to set up a solar plant, and but there were issues. In semiconductor, unfortunately, in 70s we used to have a lot of companies there, but I do not know now. I think what has changed, maybe the infrastructure is not there. You don't have they figure it out that we can buy it from China much cheaper. So it may not be there, but I guess it has to change. And you people have to, deal with Prime Minister, with the authority that in India should have that, because it's important India should have that.
Yeah, and there is another question that why India is not showcasing novel and path-breaking research like we see in the foreign top universities.
Really, I'm not able to get the question properly. Something you have writing.
So are you? Am I audible?
Something is the sound is not clear. I do not know what the question here is. Something you could share your screen. I can read the question.
So can you hear me by the way now?
I can hear you.
Okay. So why we are lagging in terms of research, novel research in India compared to
So,
foreign
okay.
universities?
I might annoy, my answer might annoy, but I will have to stick to it, okay? The reason being is that in old days, for example, the promotions were very difficult, right? If you join a university, you become lecturer, and after 10, 20 years, you become associate professor, and if you're lucky, before your retirement, 2 years, 3 years, you become professor, right? But that system in India has changed. I mean, I remember when Professor Chatterjee and BHU, he produced the best people in India, and he became professor just few years before his retirement. But now promotions have become, very fast. So once you become a professor in different places, then the drive is not there, requirement is not there. In India, like example, like research scholars, they bring their own funding, right? UGC or CSIR or somebody is funding them. Many people are coming to do PhD under the UGC Quality Improvement Program. And so they don't have to look for the job, they already have a job. So I guess the requirement has changed. Plus what happens that you want to do research, and if you don't have a customer, if you know that, hey, there is nobody who is interested in my work, then you don't have the drive to go extra mile and to do things, right? That's what I said, that a partnership with the industry, if you need to have a customer, you need to have an application. I mean, if you have in the university, if you have the entrepreneurships, right, that you can start your own company, right? Many universities in the US, like Harvard, Stanford, these universities, they have a discipline there where they work with the students and encourage them to start their own industry, a startup, blah, 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 and they are successful. And I think in India, also, many times you do the world-class research, then you find that don't have money to present it, go for international conferences. I do not know. I think this is the question that you people know why it's not happening, right? Plus, I mentioned that the collaboration part is missing there. I mean, here, not everybody has personal growth facility. Somebody has personal growth facility, somebody has fabrication, somebody has device idea, they get together. I mean, when I was in Bell Labs, I had an MB machine, but I used to work with a number of people. Somebody has device idea, somebody processing, and we together, within a week or 2 weeks, we have some results. In India, you have to do everything yourself, and there's a lack of trust. People believe that this fellow will steal my work, this fellow will do that, this fellow will do that. So, those things, the networking, the collaboration, they are very important. If they don't exist, then, you have a big challenge of resources.
Yeah, one last question from the YouTube live streaming, how photonics will influence the world in the next 1 decade?
How photonics will influence the world in next 20 years?
Next 10 years.
Next 10 years. So that's what my presentation was, that number of fields are emerging, right? I mean, today we are doing this conference through, virtual conference, the broadband networking, they're taking the broadband network everywhere, fiber everywhere, increasing the speed, deployment of 5G. I think everything would be expedited now, right? We understand the need for the bandwidth. And because there's a need for bandwidth, so I think that the industry, the government, they would be making investment because the broadband has become the new highway, super highway, if you want to connect the world. A lot of, virtual learning, virtual conferences, the value has come out, right? So, people would think that, hey, we need to have it, otherwise we can't survive. So the communication, I mentioned that those areas, right, in agriculture, the healthcare, so all these fields, I think they would grow. As I mentioned that in Clio, 18 parallel sessions for 5 days, So people are working hard, and especially Europeans, they are spending, trillions of dollars, and almost every university trying to get something out of it.
So yeah, now I would request if anyone has questions or want to interact through the Google Meet Live, please you can pose your questions to Dr. Naresh Chand and accordingly interact. Professor Basanta, can you come in if you have...
So my suggestion is, after specific question to Dr. Naresh Chandra is over, we can take up few questions related to IIT and optics research. Of course, Professor Naresh Chandra can participate. That will be wonderful. We have now some questions coming to in general. Some of the questions are related to facilities in IIT also.
Yeah, but those questions we can certainly take, I think. But I think if anyone, because otherwise there are a lot of technical questions I can forward you. There are 20, 30, 40, something like that.
So there is
I had to give another talk at within 20 minutes, 25 minutes. People can send me the question through email, technical questions. But in terms of the facilities in IIT, I think the model which India should adopt is the same model which in US and in Europe people have. What they have is that, I give you example in the US and England, because the two countries I live in.
Yeah,
they have central facilities or center of excellence. So like for example, in England, Sheffield, they grow crystal for the whole country. So if you are in the universities, not everybody can afford MBE, MOCVD or whatever. So you have central facility and they grow the crystal for everybody. You have Cambridge, they make the mask for everybody. You have characterization facility, right? You have different places in Glasgow, for example. Glasgow, they have called KNT, Kelvin Nano Fabrication Technology. So you can go fabricate your mask. They have electron beam lithography. They have processing technology. I have been to that lab few times. They provide that service, right? You have a University of Cardiff. They have the world-class characterization facility. So the point is that what they have done is that they have made this center of excellence. So people can go and use the facility. So you remember that last time when we had the meeting on 28th, that Vijay Janyani from Jaipur, he showed that he has excellent characterization facility. So there is no need for anyone to duplicate that, right? See where is your core competence. So you should have really a networking, and together you are working. You will be providing the characterization, you will be providing growth, we will be doing this. So then you can move much faster and you can make things happen. If you are waiting for everything in-house, vertical integration, that will not happen. Those times are gone. You may end up your entire life and it may not happen. And the situation would be, in my village, people used to say, na hoga no matel na ladanda chagi, So that's the kind of thing. So you really have to see that where that facility exists. I mean, in India is a big country. And the government of India had made a lot of investment in number of technologies. You had to locate that. You had to ask, like in MIT, if you go to Sandeep Chatterjee, ask him, hey, tell us where we can go. We need this, we need that. And maybe they will tell you. If you feel that this facility people are not willing to talk to you, then use those resources. They can bring you together. Hey, we need this and we can't afford it. So you have to do that. And this is what they have done. That's what I said, that India should have the National Photonics Initiative. And you should have the center of excellence, that you good in this area, you good in that area, and in that case, you can combine, right? So that way things would move much faster. But so this is what I would say, that the collaboration, the industry partnership, university partnership, university partnership. And by the way, there are a lot of foreign labs, right? I mean, in India, if you really want to work in different areas, people would welcome you. Like for example, in Ireland, there is called Tyndall National Institute, right? They love Indians. I have been there a few times and I see a lot of Indians there, and they have all facilities there, right? So if you are working on something, you have a clever idea, you can go there, do part-time research there. In Belgium, there is a IMAC facility, Ghent University. They have excellent integrated photonics, silicon photonics facility. You could go there, Santa Barbara, Cornell, one Indian, Singh, he gave like $100 million to Penn State, UPenn, and they have a Singh nano fabrication facility. And what I'm trying to say that you can have collaboration across the world today, right? Facilities exist there. It really depends, whether you trust other people, you want to go there. People are eager to work with you because they feel that the Indians are smart. Indians have very high reputation, by the way. So you approach anybody that you would like to do this, but you have to live a life of gratitude. Means that if somebody is helping you, you go to acknowledge the help, you go to continue the dialogue, not just that, hey, you got the help and then you forget it.
Yeah, thank you very much, Dr. Chand, for these nice and very good suggestions, and also thank you very much for this wonderful talk. You have been always supporting. You also have been involved in mentor-mentee program and also spreading the awareness in India regarding photonics. Thank you for all that, and thank you for also accepting our invitation and giving a wonderful talk. So with that, I think since we can also take some of the questions that Dr. Barua said regarding some of the general queries that a lot of our students, undergrad and MSc students who have posed questions on the YouTube live streaming regarding their ambitions or maybe entry into the IITs. So
in fact, any questions related to any questions that we will be able to answer, I am ready to take up questions. Already there are some questions.
I can speak out the questions and maybe one can answer if you want.
Yeah, first of all, I think Ashwini is already there. Kanhaiya is there.
Kanhaiya, I think, is not there. And maybe others also, if there are general questions, please can answer.
There is one question is, please let me know where the nonlinear refractive index measurement can be done. So Ashwini may be aware of. So we have nonlinear refractive index measurement system. I think the ellipsometry is there at CIF. I'm not sure about nonlinear refractive index measurement.
And one question is that...
Yeah, that is right. That facility is there. So that is one of the ways by which one can do the measurements. That is true.
Okay, good.
Then, yeah. So, Ashwini, so the question is whether the same ellipsometry can be used for nonlinear refractive index measurement?
Non-linear means, yeah, wavelength varies, but you need a source where you can scan the wavelength. Then it should be possible. So,
hey, Gagan, could I leave because I had to get ready for my next talk?
Sorry?
Yeah, he can leave, I think.
Could I leave because I had to get ready for my next talk?
Thank you so much. Yeah, if you wish, you can stay and you can leave also. If you are, you have another thing.
I have another talk at
okay. Thank you,
minutes.
Thank you, Dr. Chan. Yeah, you can leave. Thank you again for joining with us.
Hey, thank you very much for listening to me. It was a great pleasure talking to you.
Yeah.
I'm sorry I taken more time than
No, it's
I
all
was
right.
planning to. But
it's all right. I have sent you the list of questions that were there. There are a lot of questions. I could only speak out 2 or 3 owing to the time limit, but there were a lot of queries and a lot of appreciation. Thank you again. Yeah.
Well, the point is that you have my email address. People can always get in touch with me.
Yeah.
And I will respond to them. Okay.
Yes.
So and we can post the questions. We can because you have all the people there. So whatever general questions we can discuss and something I can help anybody. I believe that I'm quite resourceful. If somebody needs something and I can help, I will try to help. I try to put the person in touch with whosoever has the resources. So, Professor Parva, where are you from? Which university?
I did my PhD from Imperial College London. My MSc is from IIT Bombay.
Okay. So, where are you now?
He is in IIT Guwahati. He is
he's
one of the organizers of this event. Yeah.
Oh, I see. I'm sorry. I did not know. Okay. Thank you.
Yeah.
Thank you. I apologize.
Thank you.
Thank you.
Okay.
Thank
All right. Thank you.
Okay. Bye bye. I had to leave. Okay.
Bye. Take care. So yeah, one of the questions that
Yeah,
we have
yeah. So there is one question. I think Ashwini also can help. I don't know who else is there. What are the facility in IIT that can be shared with outside academicians, for example, teachers and all? So what I know, we have a central instrumentation facility where we have facilities like electron microscope, atomic force microscope, and we do allow researchers from outside. As far as optics is concerned, we have actually we do not have this facility. We have experimental setup here. We have experimental setup related to pulse deposition. I think the microphones which are not in use should be muted. Yeah. So we have right now our facilities are small in the sense we have tabletop experimental setup. We have lasers based in IIT only. We can, of course, if somebody comes, we can show them how to use the laser, but unlike the facility in some other area where there is an equipment, our most of the facility is like an experimental setup. So of course, but related to that, if somebody wants, and suppose we have like interferometer setup, we have terahertz generation setup, we have now laser cooling setup, but these are all experimental setup. We have also pulse laser deposition, thin film measurement system. So we have all these facility, or rather I would say experimental setups. And now if somebody wants to set up a similar experiment, then we can of course provide help. Now we are also, with this conference, we now also know how to send information using online means. So it will be possible, maybe we can show you the laboratory, we can give an online tour also of the laboratory, or if you come, we can definitely help you, making you understand, making you how to prepare the project, or all these sort of things. Ashwini, you'd like to add something here?
Hello?
Yeah.
No, what you said is correct. Maybe if it is also possible that, if there may be many facilities which are individually available in the labs. So those who are exploring for certain facilities, they may individually contact and write an email, and they can find out if those facilities can also be used. So you are right that CIF is one central place where all the facilities are available. But other than that, one can approach on individual basis and talk to other faculty members regarding the facilities. I think that is another thing that can be done.
Yeah. Here is one very important question. Bhuvan Daniel, the question is there any provision for outside to get help regarding, okay, that question I think I have already answered. His second question is, what is the basic requirement for students in UG and PG to pursue their study in IIT? So we have BTech in engineering physics, and to join BTech in engineering physics, the entry is through joint entrance examination, the IIT entrance examination. In addition to that, we have MSc physics program, 2-year MSc physics program. The requirement is BSc with physics, and then there is a all India level exam called JEM. So one has to appear in JEM, and then only you will be able to join IIT. In addition to that, after that we have the PhD program. For PhD program, actually one has to have most likely MSc in physics or in some related area, and if he wants to avail the scholarship, there are two ways, either through GATE scholarship or through CSIR NET scholarship. We also nowadays we are also taking up Inspire entry through Inspire. So you have to, after your MSc, you have to apply. Then at the same time you have to qualify for terahertz crystal. If so, what are the characterization technique available there? We are growing crystal in terahertz applications. I think this is the question for you.
Yeah, we have been developing terahertz characterization technique called terahertz spectrometer. So far, as such, we don't have. Hopefully, after the lockdown, probably we will have terahertz spectrometer in couple of months' time. We have all the related instrumentation that is needed for building it up. So hopefully, we will have it soon. Regarding
There is one question. Yeah. You want to say something?
One question is there, if probably regarding the internship at IITs for the faculties and maybe for the students, how to get internship. So in this regard, maybe certainly there are different channels by which interns can come. This year it didn't happen, but also I can highlight few of those. Some are there in which students can come here for 4 to 6 weeks. That's through TEQIP, TCube 3. Many institutions are the part of it. Just check with your institution. Another channel is that if they are in the Northeast, then we have a special program. They can come for internship for a month and they get some funding. On the top of that, we have our photonics chapter. We can also sponsor them through that chapter also. If you are interested, just go to the profile of the faculties and see that if they have relevant area. So yeah, these are different ways, and also by themselves on self-sponsorship you can always write to any faculty and they can hire you depending your personal interaction, like how if they like your profile or so.
There is one question, whether there are internships for research scholars.
The same is true actually for both of them. This is also internship that is also true. This is for UG, PG both. This is applicable, what I told, applicable to that also. But for research scholar, they have to find a research area that matches to their research and they can interact. Our research fields are there on the website, so please visit them and feel free to write us.
There is also a question, is there any possibility of working on optical nano antenna at IIT Guwahati? If yes, one can have the access to it. Optical nano antenna.
Should I answer or? Hello?
Please answer.
Yeah. So I don't know if you are talking about the theoretical or the experimental research, but certainly we do have fabrication facility and conducting experiment in that area about the nano antennas, even lithography and all related facility we have here. And although I personally work in the antennas at the micro scale, we do fabricate them sometimes. I have done that, but no, we do right now. But these are something that based upon your exact interest, we can accordingly collaborate or involve you in the research. Just write with the details to our email IDs. Just find it on the website.
I think this question Ashwini will be aware of, whether there is a provision of part-time PhD. So as as far as my knowledge goes, I think part-time PhD is possible. However, the candidate has to be sponsored. That is my understanding. Ashwini, you want to add?
Yeah, there is a provision for part-time PhD. Students can apply, so they can do that if they are in a service. But the condition is that they should be employed in a place for more than a year. They should be continually in the job also. It should not be that they have left the job. So yes, part-time option is there.
It should be self-sponsored also.
Yeah, actually it's like this. It's not self-sponsored. So part-time in the sense, yeah, it will be self-sponsored part-time, or if they are employed somewhere, then their employer will take care of their whatever it is. Yeah. So there are two things into.
Now another question where Kartik Goyal is looking for experimental research. So experimental research, actually we have many experimental subgroups within the optics group. We have faculty members working in laser matter interaction and in film deposition using pulse laser. We have faculty member working on optical fiber sensor. We have faculty member working on laser cooling. Then Dr. Gagan Kumar is working on terahertz, and myself working on computer generated holography, optical microscopy, and optical filter. So you have seen Professor Dholakia's lecture. He explained about optical trapping. So here we have set up a laboratory where we have demonstrated optical trapping for small beads in an experiment. So here one PhD student. So yes, of course, we actually we are several experimental subjects within the optics.
Okay, if any more questions are there.
There are many more questions, but so all the questions we may not be able to answer. There are questions related to UV, the effect of UV. Let me see.
Apart from the technical, I think technical side questions, they can always email us.
Yes. So we want to take up non-technical questions, means IIT related. There is a question, is there any visiting student program? I think Gagan has already answered partly, or you want to add?
Yes, there are more. In fact, if you visit the CET website, Center for Education Technology website, you will find that there are several. In fact, one is that I have already answered, that is one is internship program, but other than that, there are 6 months or 2 years sort of research exchange programs are there, and research collaborations are there. So even faculties or research scholar both can write a proposal jointly. They can submit here in the CET department, and they can come here for for certain period of time as a visitor.
Okay, there is another question. Can anybody from a private college join as a part-time PhD student?
Sorry?
Ashwini, is it?
Yes, they can join. They can join a part-time PhD, in which case they will need to provide a NOC, no objection certificate, from their college. But they should be employed. Yeah, they can do that. Hello?
Yeah. Then another question, is space optics also studied in IIT Guwahati? Space optics actually not as such, but part of them. For example, we have Dr. Ashwini Kumar Sharma and Dr. Alika Khare. They are working on laser matter interaction, where they study about the property of plasma that is generated when the laser hits the material. And some of these property may be useful to understand what is going on in space also, but it may not be exactly space optics. Then we also study how the laser beam propagates through space. So maybe partially, but we are not naming it as space optics. Again, there are so particularly we can see the technical questions where we do not have full command. We are not answering those questions. So if you have technical questions, as Dr. Gagan Kumar said, that you can also send email. So ellipsometry on single crystal available or not? You want to answer that question?
What was the question exactly?
Ellipsometry in single crystal, on single crystal is available.
There is no voice. I think the voice is not clear. Let me just check if I can see.
We have an ellipsometer, so I'm not the expert there, so I cannot say. I cannot say whether it will be. Okay, so whether it is single crystal or not. So I am not certain. I am taking another question. Is there any simple practical on photonics for UV level? Because we have to introduce this kind of discoveries in practical manner, means increase the creativity. So what you can do, actually, both SPI and Optical Society of America, they send some packets containing some very simple experiments. These are very interesting also. So, for example, how images form, how a microscope works, what is a hologram, but you have to form a society. So, for example, we have this SPI society and IEEE society, and it is entirely by the students. So, when we form this society, the OSA or SPI, they provide experimental, very simple experimental setup. But we also have some experimental setup. Our laboratory staff has prepared some setup, very simple setup. Some are related to optics and some are not related to optics, but these are really good communication activities related. Another question, is any ROF and POF related work going on? I do not know what is ROF means. Sorry,
I didn't, because some
is ROF or POF
Sorry?
work going on in IIT?
Somehow voice is sort of, echoing. So that's why I was not able to listen. So you can write the
It is in, yeah, it is in Google Meet comment section.
Ellipsometry on single crystal is available. Is that?
Ajay Vyas, is any ROF and POF related works are going on? Anyway, I don't know this. What is the full form of ROF? So I think the person can. Ajay Vyas is already there. You can probably speak out.
It's Ajay Vyas. Yeah, I think I didn't get the.
Those in Google Meet can directly speak out. Only thing is that you have to mute, and then once your question is over, please mute your microphone.
Okay.
Okay, I am taking up another question. Is photonic used in crystallography? So, from my experience, yes. Photonics is useful in crystallography. Already in one of the talk, Professor Sudipta Maiti, he showed the high resolution application using laser. So one can actually image the crystal also. And Professor Stephen Hell of Germany, he invented a technique called stimulated emission depletion microscopy. And using that technique, one can image that colloid and crystal. So already photonics has entered and it is contributing to crystallography. Another question, how to approach the postdoc position in IIT Guwahati? I think we have entry to postdoc probably twice in a year. Again, I think Ashwini will be the better person to answer. Ashwini, the question is how to join a postdoc position at IIT Guwahati.
I think I don't exactly know if it's twice a year, but usually I think they should look for an advertisement, which I think, yeah, it's around twice a year, and then they should apply accordingly. So they can get more details on the IIT Guwahati website, I believe, but there's a procedure that they need to follow.
There are NPDF and IPDF. There are two programs, through which people can come for the postdoc. The details are on the website here.
Yeah, details are available on the website. I don't have much information, but that is what it is. I think Kanhaiya is in a better shape to answer this question because he's also optics group coordinator.
Okay, there is another question. Is it possible to get a PhD admission for a student who has qualified only CSIR NET, not JRF?
Well, not.
No, I mean lecturership, if it's lecturership, it is not allowed. It has to be JRF.
Yeah.
Yeah, because it requires, because you get a stipend, no, scholarship. So without JRF, you cannot apply for the PhD program.
Okay, Krishna Kumar is asking when we get our certificate, sir.
We will send an email soon to all the registered participants regarding this and how to get it.
So definitely you will get the certificate. All those who have participated either through Google Meet or YouTube, you will get a certificate. Probably you want to set up we want to set up the website, or we don't want to declare it today.
I think what we had decided with these student organizers, maybe we can email them with specific instructions, getting their opinion and feedback. So we will soon email you tomorrow, hopefully. We can discuss with them.
Okay. Yeah. So can you suggest a textbook or reference book for theory and application of nanomaterial for beginner? Ashwini, do you want to suggest a very nice book for nanomaterial for beginners?
Yeah, I got disconnected. What is the question? I got disconnected.
Any good book for nanomaterial for beginners?
That is difficult to say because this is a very specialized subject. So it is difficult to say if books by Indian authors are available on nanomaterials. I don't have any idea about.
Okay.
Hello.
And there are many questions on nanomaterial, but I don't know.
Yeah.
We are, at least myself, not having expertise on nanomaterial. Yeah. Somebody like to.
Hello.
Yeah.
Hello, sir.
Yes.
Can I ask the question?
Yes.
Sir, I am Bharat from Anna University. I had a question with ellipsometry studies.
Yeah.
So whether your unit in IIT Guwahati is working with single crystal ellipsometry or thin film ellipsometry, I need to know.
Yeah, we are using thin film ellipsometry. So.
Sir, whether it is possible to take single crystals of some 3 mm thickness single crystal is possible, or only it is allowed to take for thin films alone?
See, 3 mm I'll have to see, I think should not be a problem, at least because 3 mm is not that big a size, but it may be a bit difficult. We have been using it only in the thin film configuration most of the time. Okay, so I think 3 mm may be slightly on the thicker side. I mean, difficult to say, but let me explore that. Yeah, let me find out.
Okay, sir. Thank you so much.
Yeah.
Okay, I think there are many questions, but probably the time is also, it's already 6:10. But since all of you have seen this particular YouTube channel, so probably we'll try, if any optics related important video, if it is there from the optics group, so we may try to use it as a channel for our optics group. So we are very excited to see your interest. I have seen that many people have already viewed the session 1. I think more than 4,000 has already visited. There are many questions actually, but it may not be possible for us to take up all questions. And also we do not have expertise to answer all the questions. Gagan, you want to take up some questions?
I think with that, I think we can end this session the 2 of this symposium. and with the thanks to all. And in the end, I would like to invite Miss Deepti Mahato, if she is available. Deepti. Yeah,
Yes,
could you
sir.
please come in and
Yes, she is there.
okay, great. So yeah, then could you please come and for the vote of thanks?
Yes, sir. Good evening to all of your respected faculties, speakers, and participants. As we come close to today's virtual symposium on International Day of Light IDL 2020, on behalf of SPIE Student Chapter and IEEE Photonics Society Student Chapter, IIT Guwahati, it gives me immense pleasure to deliver the vote of thanks to one and all present. First, I would like to thank all the faculties of Optics and Photonics in the Department of Physics and the Department of EEE for their continuous support and advice, which have helped greatly towards the successful organization of IDL 2020. I sincerely thank the Advisory Committee for their valuable suggestions to organize such an event on a virtual platform. I am also thankful to Professor Shubhradeep Ghosh, HOD of Department of Physics, for his presence and the encouragement. I sincerely thank all the speakers who kindly accepted our invitation and shared their knowledge with us. I thank Dr. Ranjan Singh for a very informative presentation on the topic of topological photonics for 6G communication. I am extremely thankful to Professor Shudipta Maiti for an illuminating talk on high-resolution microscope using laser, for shedding some much-needed light on happiness in the gloomy hour. I also wish to express my heartfelt thanks to Professor A.K. Mahapatra for an effective session on the topic of dynamical phase transition in MOPO. I extend my sincere thanks to Professor Martin Booth for an elaborate and very informative session on adaptive optics for aberration correction in film preserving laser. My sincere gratitude to Professor Kishan Dholakia for a wonderful and detailed session on optical trapping. I also wish to express gratitude to Professor Brian Pershaw for giving us a glimpse of basics to advanced topics in photonics. I thank Dr. Naresh Chand for an extremely practical talk on vast opportunities that photonics provide and the challenges that we can look into. It was indeed a very inspiring and definitely informative session we had today. My sincere thanks go to the whole organizing team and all the members of SPIE and IEEE Photonics Society student chapters for the tremendous efforts. I would like to mention Rajnandan, Rakesh, Partha, Angana, Dhriti and Akankshu for their continuous hard work. Now I take this opportunity to thank Professor Basant Ranjan Barua, Dr. Ashwini Kumar Sharma and Dr. Gagan Kumar for chairing the technical sessions. Unfortunately, Professor Amarendra Kumar Sharma could not join this event. We remain grateful to the faculty advisors of SPIE Student Chapter, Professor T.M. Dey, and faculty advisor of IEEE Photonics Society Student Chapter, Dr. Gagan Kumar, for their constant guidance. I thank Dr. Kanhaiya Pandey for providing a brief introduction on the research that is happening in the optics group in IIT Guwahati. We are also extremely thankful to the computer section of IIT Guwahati for providing the internet facility for this event. Lastly, considering this unprecedented situation, it was indeed overwhelming to witness such number of active participants. I thank all the participants for making this event successful. We hope that the sessions were helpful in a way or the other. Once again, I thank the organizing committee for their contribution that has made this virtual symposium a successful one. Please stay home and stay safe. Thank you.
Yeah, thank you, Deepti, and thank you very much. And yeah, it has really been a wonderful experience for all of us, and organizing this virtual event for the first time. And already you said thanks to all the important people, but I still would name again the Rajnandan, Rakesh and Akanshu, who has been really working hard in last 1 week, and also they are not here, they are behind the scene, and thanks for making it happening. I think.
So this is our
yeah.
first YouTube experience. So you might have seen some glitches in the beginning, and the person behind the YouTube is Akankshu, who is doing it from somewhere in Uttarakhand. He is managing all this through his mobile phone, at the same time doing work in the field probably.
Yeah. So these three people have been working hard, obviously, and so that's why. But anyway, it was a wonderful experience for all of us. So I think we can end with this thing, with this session also, and this entire one-day event. And virtually all are invited for tea at home. Thank you. Yeah, this is all. Yeah. Can we end now? Thank you.
Thank you all the participants.
Hello? Yeah.
Yeah. Thanks to all the participants,
Yeah,
both in
thanks.
Google Meet and in YouTube.
Yeah, although it's a virtual tea you can take at home, but whenever you visit IIT, tea is pending for all the people.
And so many participants are asking whether we can provide the PPT. Actually, we do not have the PPT, and in fact, we didn't request the speaker to provide us the PPT. So PPT we do not have. However, the recording of this talk will be available in the YouTube website, in our YouTube channel. So if you go there to our YouTube channel, IDL-2020 IITG Virtual Conference, then you will be able to see recording of both the sessions.
Yeah. So that's it, I think. Thank you. Thank you all. And take care. Stay safe.